And here you can see some more. And in fact, industry is also looking into these open source tools, because considering the prices of this tool, people wants to try out these open source tools, because, for example, Synopsys design compiler can cost you around $100,000 or $70,000. I know $70,000 was the price like around 10 years back. It could be now $100,000. And at the same time, you have a processor design tool. This is also a tool chain developed by university. Actually, it's a temporary university from Finland. So where basically you can design your processor core, you can customize your core, and it's free. The similar commercial tool is available by the Synopsys, and I'm pretty sure it cost quite lots of money. So basically, I want to say here, like, you can rely on open source tools. It's not like you have to have these commercial tools. And personally, I have tried Yosos on my own. I have tried this OpenASIC processor design. I haven't tried other tools like, for example, OpenSTA. At the same time, you can see you can get this PDK also. So PDK is a library, it's the foundries which provide, and that's basically input to a EDA tool. So you can see this Skywater PDK. This is another you can download. I personally never download, but it's on my agenda actually. So basically here you will see you get the design library, which can you feed in again to a commercial tool or open source tool, and you can design your stuff, implement your stuff. I don't think so that can be, and I don't think so that's a showstopper. And to my knowledge, the local universities here and some even standard companies, they have tried those PDKs. They actually fabricated some chips, measured those chips. So it's something which is, I think, it's in kind of a mature state so that people can use it. So this is a cliche slide. Probably you see this tool flow or ASIC implementation flow many times. So people begin with this RTL. I intentionally did not put the common slide, but I have put here the slide which I go through, or the process which I go through every day in my at my workspace. So basically, you start with the RTL. That's basically your design. It could be VHDL, Verilog, any format. So as soon as you have the design, you basically get two paths. One goes to the FPGA synthesis and prototyping. Many companies, they go for FPGA synthesis and prototyping for early software development. But if your chip is really small, which is basically less than 10,000 of instances or something, you're on mature process, you know what silicon process you're using, then probably people cut this corner. But if you're really on high-end process like 32 nanometer and below, then people go for FPGA synthesis. And if you're developing processor or something, then you need early software development. So this gives you path for early software development. And then I mostly work on this ladder since last 10 years. I've been here for some years. But here then you take this RTL, and that goes for logic synthesis. Logic synthesis can be done by various tools, as I shown here, like the red color is for Synopsys, blue color is for Cadence, and Siemens is in purple. So you have tools available here. Tessent actually don't do real logic synthesis. It perform more test activity. So what actually here design compiler takes is your design in the form of RTL plus your constraints, which I will discuss after a couple of slides. And then it knows like what is your design look like, what your off-chip environment look like, and then it will basically perform synthesis. That means it's from software point of view, if you see that you write a code in any software language, it gets compiled and get boiled down to assembly code. Or so here it's your design that gets break into standard gates. That could be your registers or flip-flops and or gates. And if you have some macros, for example, voltage regulators, power switches, you have a model for that. So it keep that as an untouched and just keep the connectivity. So basically you have a connectivity and the timing information here. So how fast your design should run, who is connected to whom, uh, and what is your gate count. That basically indirectly gives you your area. The clock gives you approximately what speed you're aiming for. And then it gives you a gate level netlist, which have building blocks of digital design, basically flip-flops, gates, combinational gates, and third-party IPs or cores like memories, voltage regulators, power switches, everything. But you don't have a wire information. I mean, so you just know virtually how they're connected, but you don't know like how far they are. Like if you have a register at lower left corner, that register is talking to another register that has to be most likely in lower left corner, but it could be like in the middle, in the center of the chip. So that topography is not really known yet. So basically wire lengths are not really known. So connectivity is there, but we don't know how far each other from there. And we need that information. You will see that later. So once we have a gate level netlist here, we perform simulations. The simulations we are performing at RTL level. So those are mostly functional simulations. Oh, yeah, but I think before that, you asked me about I2S. So the I2S is actually a digital protocol. It's developed by Philips. So it's similar to I2C. It's a two-wire protocol. It's mostly used for data transfer and mostly in audio domain. So it has a left channel and right channel. So it can pass digitalize data for a left channel for some time and right channel for some time, and it's keep on doing that. So basically, you can treat that as a protocol, especially made by Philips for audio transmission, audio signal transmission. Okay, back to this tool flow. So now you have a gate level netlist. You perform those simulations which you have performed at RTL level. They should run. They run on RTL level exactly. If there is some problem, then you have to look into synthesis, what can go wrong there. But most likely, as I said, like it's just breaking down your behavioral code or structural code into standard gates. So that mostly works smooth. And sometimes people cannot run all test cases, or people still be paranoid about this synthesis tool. People wants to check. Basically, the companies which perform like very specialized ASIC, and they have those ASICs for more than years. Like for example, if you consider mobile baseband processor, which they just work incrementally and they work on only one chip. So basically, they want to perform this RTL is exactly same as this synthesized netlist. So they perform some kind of formal verification also. So formal verification we will look after some time, but that's basically equivalence check. Functionally, this RTL is exactly same as this gate level netlist. I will show you in detail how it exactly look like. So that's basically test verification, test independent check. Like you, whatever you're feeding, that function, if this function is doing addition, the netlist you are getting is also performing same addition. It's not doing anything else. So that we do in gate level simulation. Of course, then gate level simulation goes into physical synthesis. So physical synthesis is basically a place and route where we actually see the physical nature of the chip. So basically, how it looks like, what's the width, what's the length, how pins are placed. Sorry.
No, continue.
Yeah.
Yes. Parkaya sir, can you please mute everyone so that we won't get disturbed in between?
Okay, ma'am.
Yeah, it's fine. Yeah. So a physical synthesis.
Okay, I have muted all other participants. Hello, Sagar. You are also muted actually, so unmute yourself.
Yeah.
Okay.
Now I think I'm audible. Yeah.
Yes.
So basically, at physical synthesis, you get the physical view of the, or you settle on the physical aspects of the chip. So length and the width and the pin placement, where pins are placed. And so basically, you are pretty close to the reality now. And then after physical synthesis, you perform some sign-off checks. Sign-off checks, as I said, like the whoever foundry that's going to fabricate your chip, that could be, okay, if you're a big player, like it could be TSMC, it could be some SMIC, it could be any foundry basically. Intel or Intel normally don't do fabrication for other companies, they do it for themselves. But yeah, that foundry has some limitations, and the limitations is in the form of like how fine wire they can carve on the silicon. If there are two wires, how these two wires should be placed, how much distance you should maintain between them. So these are the requirements basically as a sign-off check. Basically, what you're going to give foundry, that's basically implementable. So, and that's people, they call it as a DFM. It's designed for manufacturability. So what you're designing is a manufacturable. You can manufacture it actually. The star which I have given here, basically at this point we perform not only logic synthesis, that means translating your logic into the gates, but we perform scan insertion. Scan insertion is a test feature. Basically, after you get the chip, you want to perform that chip is functionally working. Of course, the one way of testing chip is like you run again those test cases on the chip, and then if your test cases has if your tests are passing, then chip is passing, but that cannot give you guarantee 100% that everything is really working, because maybe your application is not really simulating all type of scenarios in real life you will face. So for that, here there is a structure called scan insertion. We will look, I will say quite in detail, I will show what scan insertion is and what tests look like. So as I said, like PDK, it's a physical design kit, acts as a critical bridge between EDA tools and the actual fabrication process. So basically, it tells you like all the standard cells, flip-flops, registers, what you're going to use, what are the characteristics of those standard cells, like how they look like physically, like what is their width, what is their length, what kind of power requirements are, what kind of timing behavior is, and what is the functionality of that chip. So if I just, for example, take AND gate here. So for AND gate, they will tell me the length and width of that AND gate. Of course, it's made up of the transistors, and then they will tell me in the timing model that how timing model looks like if you stimulate one input of an AND gate, how much time it take that stimuli reflect on the output of the AND gate. Power, like when these transistors will move from charging and discharging, so how much power basically they are consuming, or in the form of current or in form of watts, if you know the voltage and current. The functionality, what that particular block is doing, as I said, like if it is AND gate, it's let's say 2-input AND gate, then it's like 2 inputs and the ANDing operation. So it will have a kind of a truth table. So basically, based on these two inputs, what your output will be. So that's basically a technology file. The parasitic extraction, I will show you. This will tell you the parasitics around those inputs and outputs we will see in the AND gate. I will show you with the example with the inverter. Design rule checks, basically geometric limitation, what you can do and what you should not do, because process cannot handle it. Hard macros and documentation. Hard macros, basically library will not provide, foundry will not provide you only registers and the AND gates or combinational gates. It can provide you a lot more things. It can provide you, for example, memories, ROMs, some custom analog blocks, for example, oscillators, amplifiers, you name it, basically. So basically, a foundry don't design it. So like other companies, like for example, ARM or companies like us, they will develop some kind of A to D converter. For example, if that A to D converter is designed using that foundry, if it is working fine, and it is characterized, then that foundry will take into their library, and basically other people's, they can take that IP, basically buy that IP. Basically foundry will sell that IP on behalf of you. Of course, you get some royalty on that one. So basically, this kind of information is provided in terms of physical design kit, and that's basically input to one of the input to EDA tools. And that could be, now these formats, they are standardized. So that's why these open source tools are coming into the picture now, because these file formats, they are not like proprietary file formats of some Synopsys or Cadence. So basically, you have a file in a standard format. It's open ground. You can write your own EDA tool as well. So as I said, like even okay, these standard foundries like TSMC, SMIC, or any other foundry for that matter, they will not share their PDK, just open source. But there are some, for example, the Skywater, it's along with Google. They do share their libraries, the open source libraries. So you can take it. I can see this is basically a same library, but different flavors. I believe LP stands for low power. And then in that, you will find maybe probably you have to download and install it. So take is basically, this is technology left where they have a geometric limitations of their timing. Basically, as I said, like whatever cells they have, it's in .lib format. I will show you that format later. So they will basically write behavior of their standard cells into this format so that EDA tools can read it. So basically, as I said, like you have open source tools and open source libraries. So nothing is blocking if you want to implement anything at your end without any commercial tool. Yeah, so here I said like PDKs have a, for example, okay, I have taken this simple example, inverter, for example. Inverter have, of course, made from MOS transistors, depending on what technology you're working. Like if you're in nanometer range, I mean like 180 nanometer or something, people normally use CMOS. Or below 180 nanometer, I think there are other technologies like, for example, FinFET technology, which goes below 180 nanometer. So basically, transistor implementation is pretty much same. You see, only there is little difference in a fabrication process, but that doesn't really bother you here, because what really bothers you, timing information and the geometric information. Because end of the day, it's their responsibility, not their responsibility, but the foundry has a manufacturing limitations, and that's why, for example, this yellow color thing is a drain in CMOS technology, but in FinFET technology, they have like these fins. Why they need it? It's There is a physics behind it. I don't know really. And if I don't know, I will frankly tell you, I don't know. The red color is the gate. And basically, as I said, like they will characterize this standard cell. Okay, now not to confuse you, this I'm showing here inverter. You please look here also inverter. So this inverter, they will perform some input transitions and observe all output transitions and then the major delay and put that everything into .lib format. And they will write the function also that say like if you give me input, the output will be the inverted A. So this kind of information you will get into .lib format, which I just show you. And then how this physically cell look like, because when you will go actually in physical domain, you have to place that cell on the floor plan. So they want to know like this, for example, most cells are rectangular shape. This rectangular shape cell have a certain width. So that much area is already occupied and the pins are placed, let's say, at this coordinate. So we know like where I should lay out my metal in order to make connectivity. I will show you that also in detail. But so what I want to say here is basically you have a timing information, functional information, power information in .lib format, more geometric information in the .lib format. So again, the PDK will have a different flavors of the standard cells. If I call the inverter, for example, you will have a different types of inverters. Basically, they are doing same functional job, but it's a different feature. So if you see, it's a 2x, 4x. So basically, it's a drive strength is different. So this inverter can drive this capacitance, but this inverter can drive this capacitance quite fast. So basically, you can say this is a fast inverter, this is a slow inverter. So the inverted output may look like this. Now you can see if we talk about CMOS, you have a pull-up network. This is a PMOS is a pull-up network where this capacitor will get charged when you put 0 here. And when you put 1 here, this capacitor will get discharged and you will get 0 here. So this sometimes basically for clock, we need a balance cells. So these cells are designed in a way so that the response to the rising transition and falling transition is same. So basically, if this inverter, if imagine this is a clock, if this clock goes through, for example, this balance inverter, it will get little bit drifted because of the delay, intrinsic delay of that inverter, but it will maintain the duty cycle. And that's how we want to propagate at least clock signals. If you use other inverters, you will see little distortion because maybe this PMOS is little bit, the holes, they have a lower mobility than electrons. So basically the falling transition, so it can discharge fast, but it's taking time to charge. So that's why the rising edge is drifted. And of course, then duty cycle is changed. Similarly, you will have cells designed for different threshold voltage. So basically how fast they will act. I have not shown here, but so basically your library is made up of many cells, many different electrical characteristics. Some are balanced, some are not balanced. And we will use those cells like wherever they are fits best. For example, balanced cells, they should go into clock tree. These cells, otherwise they should go into the path. Again, then you have a low drive strength, low drive cells. So basically the width of transistor is small. So obviously the physical dimensions are small. So which cell you should use, whether you should always use small drive strength cells or high drive cells, we will see that later. Both have a pros and cons. But basically you see this kind of information you get from your foundry, what they can manufacture for you. And similarly, you can get information for other hard macros. Those not necessarily digital. For example, you can get similar information about A to D converter. So there they will have like maybe not functional information, but how the inputs look like, what input insertion delay is, what is the physical size of that cell. So basically, you have all this information so that all these EDA tools know like what are the sizes, what are electrical connections, what are electrical delays of those building blocks, and they have to work with those building blocks in order to build your chip. So far, so good. Okay. So design, this is again more cliche slide. So of course, you know, probably there are RTL design. You can implement your RTL blocks. Those could be state machines, controllers, or standard IPs like I2A, I2C, I2S. So basically, whatever design you want to implement, whatever you are implementing, and those are mostly you go through undergraduate courses, like where you do actual RTL implementation. That could be a counter also. So basically, digital design is depend on what your functionality is. It could be a simple state machine which is controlling some sensors. So basically, I don't have much to say here. So RTL code is RTL code. So something which you want to implement your functionality. But whatever you're implementing in industry, that goes through the code quality check. So basically, you have a freedom to write your code as a software engineer. Some things like EDA tools can handle, but still it's not recommended. You should still follow the electronics motivation behind that. So basically, you should, even though you are writing RTL, you should think in terms of clock cycles, how data flowing, how the structural data flow graph is basically. But that will give you more functional information, like Boolean information. Like if I talk about if you're making, let's say, only AND gate chip, nobody will do that. But I'm just saying, like if you have two inputs and one output, and your functionality is ANDing. So your RTL code, you will write it, but you still not provided like power information of that chip, whether your chip is going to get supplied by 3 volt supply, 1.8 volt supply. So that kind of information we will provide by either UPF format, CPF format. This unified power format, it's a common power format. Earlier there was two power formats developed by Synopsys. UPF was developed by Synopsys, CPF was developed by Cadence. Eventually, they standardize on, they convert those two formats and they standardize on UPF now. So basically UPF, you can say it's a industry standard format. CPF is still accepted. And it's basically same information. I will tell you what exactly it looks like. But basically, now you have your RTL code, your power structure of that chip, and your timing information of that chip. That's what you need. And that goes to some tool called Spyglass, for example. This is not necessary every company goes through this step. Some people, they cut corner because if their blocks are mature, if these RTL blocks are mature enough, they cut this corner. If it is relatively new or you are really working on some specialized processor, baseband processor or something, they really want to be fine-tuned. So basically it goes to the Spyglass. In the Spyglass, it will perform some lint checks. So basically, if you're writing some code which is ambiguous, so the tool will perform some cases and give you warning and will tell you like, okay, you have written something like so and so. It's hard to interpret, but I'm interpreting in this way, and that can result in mismatching your RTL simulation and gate level simulation. So that's what I mean to say here. So here, if you see, the simulation is working fine here, but not working fine here. So that means you have written some code such a way that this tool have a hard to understand that code, and then it performing some kind of assumptions. Of course, it will warn you in the log file if it is making any assumption, and it will explicitly tell you like this assumption can result into mismatch in the RTL simulation and gate level simulation. So basically, you should not overlook those warnings. We will see in that process. We will see in this stage what exactly those warnings look like. Then again, it will look for your clock domains. Of course, you will have a multiple clock domains. So if the data is moving from one clock domain to another clock domain, how it is synchronized, because it's a basic principle of these digital cells, basically flip-flops, that you have before a clock age, you have a setup window and the hold window. So basically your data should not toggle in that fine time period. Otherwise your flip-flop will end up into metastability. And metastability means your flip-flop will be, the output of your flip-flop will be neither logic 1 or logic 0. It will be intermediate. I will show you exactly in detail what exactly I mean to say that. Same applies to reset domain crossing checks. So basically, if your reset pin also has to respect the time. The testability, that means your chip should be testable. That means you should have a full control on the reset and clock. So basically, you should not have only software resets, and then you cannot control your chip from the top level pins, because tester can access only top level pins. The software reset is actually more software functionality. A tester don't have access to that feature. Power constraints and quality checks. So whatever power structure you will implement, that is the integrity of that power structure is correct. Timing constraints. So basically, it will tell you your timing constraints. They are consistent, and then they are not contradictory to each other. So contradictory to each other in the sense, like for example, if you define the input delay on one pin, and then again you said accidentally that I don't bother about input delay, I false path from that input, and then tool will say like, you're giving me contradictory input, you're setting input delay, that means you want to meet timing for that input pin, but at the same time you're saying it's a false path. So tool will always do more pessimistic assumption. So even you will say like, I don't care about that timing, tool will say like, I do care about timing, because I will consider pessimistic scenario here. So this is about RTL design. So this is RTL design is basically you can write your any type of code, like it could be, if you're working with processors, you could write your square root module, which can perform square root operation, floating point multipliers, floating point dividers. People make big deal about those blocks because those blocks takes more than one clock cycle. People want to have these blocks fully pipeline, so that it will not create blockages in processor performance. As an aspect of that one, I will tell you about this ASIP. It's a application specific instruction processor. It's not just processor, but application specific instruction processor. Again, this is the open source tool. As I said, like this tool I'm talking about, as I said, like you have a commercial tool from Synopsys also. I don't have in my head name of that tool, but this tool will give you your customized processor for your given application. So in general, we know like when we work with the processors have lots of ALU. ALU have lots of instructions. Processor maybe have a DMA and or other functional blocks, which probably, for example, you don't want to use it, and you have to still carry that burden with you. A burden in the sense silicon area, because silicon area costly. So now people come with this feature or a processor called instruction specific. So that means based on your application, you will write architecture. So here you see I'm sorry, here you see a basic architecture where you have a GCU, global control unit, some local registers. You can act as a treat this as a cache or a local memory, or fast RAM, which is inside processor, ALU, which is performing addition, subtraction, multiplication. And if you're good with addition, subtraction, multiplication, you don't want to carry unnecessary shift operators or floating point multipliers, floating point units. So basically whatever you need. Then load store unit, of course, your processor needs to communicate with the data memory and the program memory. So basically this is a tool flow, as you see in the flow chart. I hope it's readable. So you start with the requirement. Requirement is any C code. So in this case, it's a CRC calculator. So CRC is like you will input some data, you have a polynomial. Based on input data, you will calculate the CRC and you will append that CRC and you will send your data, transmit your data, and that data will get received by receiver somewhere. And then receiver perform again CRC operation and it will make sure whatever it has received is correct. So basically this is the application. So job of this is only performing CRC calculation. So, and this CRC calculation can be done by, for example, this C code. And that C code is compiled by compiler called LLVM. This flow is completely developed by a master thesis student, actually, in a Tampere University in Finland. So basically, this compiler will compile your C code and will give you, of course, it will compile, cross-compile, not compile, because normally whenever you compile your any C program, it will get compiled by GNU compiler to your processor in your PC workstation. But here it's not compiling for workstation, but it is compiling for this architecture. And you are saying like, okay, I have this ALU, now I have only these instructions in my ALU, and I have global control unit, and I have these registers to work with, and I have load store unit, which is connected to the memory. So basically, this compiler knows like what resources you have from hardware point of view. So it will generate a compiled code for you, and then it will simulate that on this this hardware, not your computer hardware or not your workstation PC, on this hardware. And then it will tell you a kind of statistics like how many instructions, how many clock cycles I need, and who is basically blocking me if you want to improve the performance. So basically, this is the tool chain of a processor design. You start with C code. You enter your architecture in a tool called processor design, PROD in short form. You compile your C code with this architecture with LLVP, and that give you statistics, simulation statistics, and then you generate RTL of this processor if you're happy with this performance, and that gives you RTL. And then that RTL you will implement into either FPGA or you go for ASIC. This is in university area, but many companies, they do work on it. For commercial purposes, companies demand for risk. Okay, this is also, it supports RISC-V instruction set. And you have a possibility. It's basically sandbox for you. You can play with this processor design. So you can add your own instructions, customize instructions. I will show you in some next slides. So, but basically this is a sandbox or for you if you want to develop your own processor, or you can just play with this existing manual, and you can get quite in depth about processor design. So here you see this C code. It's simulated for this architecture, and this architecture looks like this. It's a 32-bit CRC. It's application. You have only one bus. This is black thing which you see. You have one global control unit. That's basically taking care of pulling in instructions, maintaining program counter, stack operations when it use load store units. You have two register files, basically temporary RAM for you for your processor. One arithmetic unit, so here it performs some addition, subtraction, some logical operations like equal to, greater than, and so on. And load store unit, so if you want to work with more if you want to work with the data and your all registers are occupied by data and nothing is stale here. So then in that case, it has to load that into your data memory and use register for current calculations. So these are the commands for these tools to compile the source code and then simulate it. And after simulation, you get this kind of utilization. This is utilization of this hardware, for example. Then it gives you statistics like B1 bus is utilized 87%, then load store unit is also utilized. And ALU is also how much it is utilized. And basically, you can modify the performance. One way to modify is by modifying this C code itself, for example. But maybe your C code is like good enough. You don't need any scope or okay, basically this is out of scope. Only you can perform any optimization on hardware level. Then what you can perform optimization, because basically you can see there is only one base. So basically when you are performing load or store operation, your ALU cannot work because your ALU cannot fetch or read any of these registers. Or when your ALU is working, your load store unit cannot really perform. Your ALU can read only one register at a time because you have only one bus. So even though if your instruction need two operands, you have to fetch like one operand first, second operand first, perform, execute, and then store it again, and it's taking long time. So then basically how you can improve, you can increase number of buses so that it can introduce some parallelism, load store operations you can cut down by increasing local memory, RAM memory, so that you don't need to perform this load store operations too frequently. Your ALU have a bottleneck, for example, because your ALU have a basic functionalities. And for example, here there was in this code there was one operation where it was changing LSB to MSB. And to change that LSB to MSB, it was using this shift by one operation many times in a loop. So basically, you can, like, okay, this is a simple shifting operation, and it's performed by some logical operand or logical instruction called SHRU, and it's taking a long time. So you can basically optimize that away. And then you can still, you don't want to. Okay, one can directly implement everything in hardware. You can even implement that polynomial in hardware, but then that you lose the flexibility that hardware software co-design is giving. Because if you write this code, even though if you change your polynomial, your CRC chip is still intact. You're just changing polynomial. So basically, these kind of things. Then I changed this based on this manual. So basically I'm referencing to this repository. You can download it, you can try it yourself. So they change it. They add one more ALU here. Not one more ALU, but they add some special functional units here. They add this reflector where I told you the MSB becomes LSB, that operation they are changing. Number of buses they have increased. Now your architecture is increased. So basically your silicon area is increased. But now you get some performance boost. So here you can see, you can do it on your own, basically by downloading this from GitHub. You start from this basic architecture, start ADF. Then you improve that to large ADF with 3 buses. Then you see instructions count. Actually, this is instruction count. suddenly becomes half. Then you add couple of extra registers, then you cut down your load store operations, then instruction count is even become less. Then you add new ALU, then suddenly become even 10 times less. So this is one is basically, it's a starting point, and this is improved number. And if you add customization, then it's even becoming, here you're not adding 3 buses. So you're just keeping 1 bus, but adding customized block. So bus is still problem. That's why here 1/3 improvement. And if you add this large custom operation where you have a buses also, so that is basically here you have 3 buses, all this, then you can see 25 times improvement in the instruction count. What I want to tell you here, basically, no commercial tool is no showstopper. Am I too slow, or shall we continue like this pace? It's 1 hour past. Okay, I will continue. So similarly, then why people are investing this special IPs or something like that? So basically, if you have any application A, which is running on processor P, and 30% of your code is like a square root operation. Basically, it's a machine learning language code where they perform lots of square root operations. So 30% of your code is a square root operation. So what will happen if that square root operation block is, you will improve and make it 2 times faster. So basically, if you apply this Amdahl's law, so 70% of your code is unchanged because only 30% is performing square root operation. So 30% of your 70% of your code is unchanged, 30% is improved by 2. You get 17% of improvement in your time, in your performance. So everybody is actually investing into writing their fast square root operators, floating point multipliers, floating point dividers. Even 20 years back, my master thesis was about floating point divider using Newton-Raphson process. So basically, these blocks, they are still mean a lot, and there is a big room for improvisation. Again, the machine learning context, which you heard many times, this is rather old concept. Neural network, you have a input layer, middle hidden layers, and the output layers. So whatever your input is coming is a sitting on input layer. You have weights. So these weights will get multiplied on this input layer, and then it goes into the intermediate layer or hidden layer, and then it propagates from hidden layer to the output layer. So basically, you heard many times, I believe, about machine learning. People broadly call it AI also, but I think that's not really correct term. It's more machine learning. So here, basically, you want to get this weights. So basically, if your job is, again, this is something which I tried on my own. This is our like validation or feasibility study project, you can call. So basically, this is application of image processing where you have around 70,000 images, handwritten images in 28 by 28 pixel format. And you basically take those images one by one. You start with random weights in the beginning. Of course, everything starts with the Python. You start with the random weights, this weights. You take one image, you see based on this random weights, what this image is classified as. If that classification is not good, you go back, you adjust those weights. So basically what happens, it does into iteration. Like if my training data is, let's say, 50,000 such images, I will make one iteration of a 50,000 images with given weights. And I will say out of 50,000, how many are classified correctly. And based on, and how many are not classified correctly. And I will generate a error matrix. And I will feed that error matrix, and update these weights. So second iteration, again, those 50,000 images will go. And then again, I will see like this time how many images are classified correctly. So maybe in first place, like out of 50,000, only 10,000 passed. So after this feedback, maybe 15,000 will pass. Then you will iterate again for third time. So maybe again 20,000 will pass. Again, same iteration. So you will go up to the level where you have a close to like 95, 99% images they are passing. And that process we call as a training of this model. And after training, you settle on these weights. So you have weights and biases, which are good or which are basically you want to fulfill those images. That is training images. Then you leave those training images and then you take test images. And then you will repeat same process for test images and you will see like the test images are also passing. So that means you have a trained model and you have weights and biases and you are ready to go for either hardware implementation of this one or software implementation of this one. So for example, this is a hardware implementation. Software implementation, you already probably guessed that you will write a C code and you will have these weights in your in C code as a variable, and they will get compiled and assembled, and your executable will come out. But in point of hardware, you have those weights. So you will have these input layers. Basically, these input layers are max, which is multiplier and accumulator unit. So you read this 28 by 28 pixel image. So basically, you have 728 pixels that goes into the input neuron, input layer. Based on these weights, which you find it out using your Python simulation, or we call training, you get this hidden layer, and the hidden layer data will propagate to the output layer. And again, it has some weights. You will multiply that operation, and then here you will get what classification it will perform. So this is one area. So this is you can treat that as a more like RTL design, and we have performed as a hobby project. It's not really something which confidential or something, so I can share. So we try to play around this this architecture. So 728 neuron input layer is intact, output layer is intact. We try to reduce middle layer, because when you will reduce middle layer, lots of multiplication operation will get reduced, and we try to see how the performance look like. So you see, these are the input layer 728, hidden layer 20. This is basically default. The first, you get 99% accuracy. You have 14,000 multiplier accumulator units. We decide like why 20,000 here. Let's cut it down to 12. And then you get, okay, you reduce the architecture or the hardware, but you reduce the accuracy and so on. And the accuracy here is 95% is still good, because when you will download this, for example, from GitHub, you will see these 50,000 images is all written, handwritten images. It's all, after seeing those images, you can see like at what extent your handwriting can be a bad. So basically, I think this 95% is still good enough. You can still recognize the image as long as it's numbers. But same concept, you can basically elevate to any other image, like face recognition or some audio recognition. That really doesn't matter. But the key concept here is like, you start with some model, settle on that model, train that model. You have the whatever you want, you implement it. So that's more RTL implementation point of view. But whatever you will implement, this is again, it's a behavioral code, structural code, whatever your coding style is. But what we want here from DFM point of view or implementation point of view, you should not consume more power, you should not consume more area. So for power, what we, from implementation point of view, if you have a block, for example, if there is this is a one block which have enable, and this block get into actually some functional mode, or it does some meaningful only when you enable it. So that means all this clock network, what you see, for example, these are many flip-flops here and lots of combinational logic. So if this enable is not asserted, we don't want to unnecessarily toggle this clock, because I will show you in power reports, this costs you power. You're charging and discharging these nets. So basically what we say, like if the block is not enabled, this clock gate will shut the clock. So all this toggling will stop. So basically you are saving power. So almost this is now de facto standard in industry. If you write your RTL code, you perform your clock, you implement your clock gating, because you know better that when you need a clock and when you don't need a clock. But this is not always the case. Sometimes you get third-party soft IP. Those are IPs are also good. But if unfortunately, if you end up with the code which is not power gated, then synthesis tool will do this for you. But then you have to tell synthesis like what threshold I should see. If I find, let's say, minimum 8 flip-flops, which are toggling only in some certain scenario, or functioning only in certain scenario and not functioning at all in certain scenario. So based on that, it can insert a clock gate synthesis tool. Many people, they don't want to give this to synthesis tool to do. They want to do it in RTL itself. Again, what many people say is like, don't let the EDA tool think for you. You should think for EDA tool. Because sometimes what happens, it can do like overclock gating. So what will happen? Imagine if it perform clock gating for every flip-flop, you will get like one unnecessary AND gate for every flip-flop, and I don't think so. We really want to do it. It's basically so basically you want to trust EDA tool, but listen but verify, I will say. So basically you want to see like whether it's really paying off by introducing this extra AND gate here. Clock domain crossing. As I told you, like sometimes you have more than one clock domain. And as I told you, like for example, in this picture, you have a clock domain A and clock domain B. And clock A and clock B is asynchronous to each other. So that means they don't have any meaningful relationship between them. So, and if the data is launched by clock A, it can launch at any time. And it will happen that the data which is launched by clock A, which you see D in pin here, that's here, which is basically data launched by clock domain A. So when there is a rising edge on this clock A, your data on D in pin is changing. But unfortunately, this D in is exactly changing on the rising edge of this clock B. And as I told you, for every flip-flop, there is a setup time, a setup window, and hold window. So that means your data should stay stable in that window, which you see by a dotted line. But unfortunately, in this case, you end up here. And now, this is the behavior of a flip-flop, because flip-flop have some loops, feedback loops. The Q pin of this flip-flop, which is a DS net, you see it end up into some kind of a state which is neither logic 1 nor logic 0. It's somewhere in between. And we don't want to propagate this state of logic through this combinational gate. That's a disaster, basically. We don't want to. Because then you will go into completely unknown state where you don't know what's really happening here. And it's a characteristic of a flip-flop. It will stay in this state only for a certain time. And that time has to be less than this clock cycle. So if you go into metastable state, for example, this point, it should eventually settle either on logic 1 or logic 0 because of the feedback loop inside the flip-flop. So that you will sample a real logic value. So electrically correct logic 0 or logic 1. So, and not something in between. So exactly 50% of VDD. You don't want to sample that. So people add this double flop, they call synchronizer. So what happened here, you see, on first clock edge, the first flop is sampling metastable state, but it's not propagating to a second stage. Second stage is always have a electrically correct logic value, either logic 1 or logic 0. So not necessarily that will be the logically correct. You have a rising edge here, it will settle. In this diagram, it's settling luckily on the rising on the logic 1, but it could settle on logic 0. So here you have to oversample. So people will do oversampling. So in order to capture this rising edge. But the main motivation here is basically not to propagate this metastable state throughout this combinational logic. That's disaster. So this is basically de facto standard of how to handle metastability. There are other ways also. It could be like a handshaking protocol. I have not shown that. So handshaking protocol, basically like this guy will say, I have new data to this guy will take that new data, and this guy will acknowledge that data, and then this guy will basically ready for next asynchronous data. That's pretty slow. This is quite fast. So people normally use this feature. So this is mostly a design, RTL design point of view. So we have not seen any power information. And as I told you, this power information can be handcrafted in the end, in the backend, or you can still do it at RTL level itself, which many companies do, because that's now becoming standard. So people will, like you will write a functional description of your RTL, the logical functionality, you will write a description of your power functionality. So that means they will create supply nets, power domains. So which hierarchy of your design belongs to which power domain. If you have more power, more than one power domain, then you have a power state table, like if you have 3 power domains, what is the state of each power domain, and that will be maintained by state table. The power switch, of course, you want to turn off any domain, you need a power switch. I will show you that in later. And if you're switching off any domain, then you don't want to, basically, when you switch off, in simulation point of view, we see the corrupt signal by saying it's as a X, but in reality, there is nothing called X. It's unknown signal will propagate. We don't want to propagate unknown signal. So whenever we will shut down any power domain, we will have isolation cells, so that or retention cells, so that we know like what value we will maintain even power domain is a turn off. Level shifter, like if you have a power domain which is 3 volt and another power domain is 1 volt, if data is moving from 3 volt power domain to 1 volt power domain, so logic 1 in 3 volt is a 3 volt and in 1 volt is a 1 volt. So signal should be electrically correct when it goes from 3 volt domain to 1 volt domain, and that's why we need level shifters. This is again industry standard. Nothing is really like some kind of proprietary from some commercial company or commercial tool. So you can use it. It's standardized by Accelerator. You can get like pretty good information about this, what exactly our domain it means. Like you can see, this is how you build 2 domains. You divide supply sets. Then you will assign those supply sets to certain blocks. I will show you in detail. So for example, this is 2 power domains. You have 2 supply sets. This logic is powered up by this P. This logic is powered up by memory supply. Then this is a power state diagram, how it looked like. So in normal mode, everything is on. In sleep mode, memory is on, but primary functionality is off. So you want to just retain memory. In hibernate mode, everything is off. So that's something which you will tell. I will show you with this example. Normally power intent, we will write like this. So this is a dummy example or made up example. So you have a chip, it has a
Hello. Hello, sir. Just unmute yourself. Just unmute yourself, sir.
Yeah, I'm first time using Zoom, so bear with me. So you was with me till up to this point? You was with me, am I right here?
Yes, sir. Yes, sir. With respect to this slide, I have one question. Okay.
Yeah.
How do you balance performance, power, and area trade-offs, especially designing during ASIC designs? Okay. Because
Yeah.
this.
So I will show you. So basically, when you will do synthesis, the tool will by default will have at a moderate level. So it will moderately work on area and power, but you can change the effort level in that tool. So you can tell the synthesis tool, for me, power means a lot than area. I can afford bigger area, but I want lower power.
And how you decide the acceptable level of optimization, that is?
The acceptable level of optimization is basically in terms of as I told you, this library will have many cells here.
Okay.
So some cells which I told you, low VT cells, those are fast cells. So if high VT cells are slow but power efficient cells. So you will roughly tell the tool I want at least use 80% of high VT cells. So that means you are implicitly telling tool, do your best, always use high VT cells, so my power will remain low. So and the tool will basically tell you okay, I'm using high VT cells as much as possible, and I'm getting this much power.
Okay.
Other area is basically how good your clock gating is. So it will tell you a report. I will show you that report also, where you can judge whether your clock gating is, sorry, I'm moving too fast. So other report is is your clock gating good enough? So as I told you here, if my threshold is 8, so it will insert clock gate only if I see minimum 8 flip-flops or more than 8, where I can insert clock gate and turn off the clock when it's not enabled or when these flops are idle, so to say. In that case, you have to reduce that threshold. So you can say okay, now I can afford more area, but I want really cut down my power. So I can afford one extra clock gate even every 4 registers. So this is another area where you can reduce clock power. Other area is more physical side, physical implementation. So in physical implementation, you can try to use again this high VT cells and some physical optimizations where you will try to use higher level metal cell, higher level metal. So higher level metal is less resistive, and basically you're cutting down power in the nets because you're cutting down resistance in those metal layers. I will show you metal layers also. So there are 2-3 areas where you want to save you can save power. One is in your RTL code itself by improving your clock gating. Other is by cell selection, what type of cell you will select from your library, high VT or low VT. And third approach in the backend, you will use a higher level of metal layers. Of course, then it will be expensive, but it will be less resistive, and then you will save power. But of course, at the cost of area, because higher you will go, your metal layers will also become more wide. Does that answer your question?
Yes, sir. Yes, it's fine. Thank you.
Yeah, and depending on actually, as I said, like in industry also, in which industry you're using. If you're working for a medical industry, let's say for example, hearing aid, uh, which uh, which you want to be ultimate low power, or for example, pacemaker, which sits in close to your heart. So, for example, so there you can, but these applications are also very very low speed application. Pacemaker, it doesn't need to work for megahertz frequency. It is good enough. It can work in kilohertz. Your hearing aid also, it can be fine. I mean, hearing aid application. Sorry, for hearing aid core purpose, it can be good in kilohertz range. But for other multimedia applications, for example, if you want to connect that hearing aid to doorbell or to your phone, then you need this low power Bluetooth and blah blah blah. So, and there you need more area or more power. Or for example, this kind of headsets which you charge maybe once a week or something, there you need uh, more power efficient circuitry at the cost of area also. So it's a trade off actually. Basically, what one hand will give you, other hand will take out. So you will get, yeah.
Correct. So what I noted that that optimization depends on the applications. Okay.
Yes, application is it's more depend on application, exactly. So more portable applications, they always strike for lower power. But if you go for example, applications uh, like mobile applications that goes into the antenna baseband processor, where they have FPGA cards, or for example, high trading platforms, which you heard probably. So they work with these FPGAs. So there they want high speed, even at the cost of higher power or higher area. So it's completely depend on application. Or for example, uh, uh, some applications, welding helmet application. So there they need high speed, because welding helmet should change the property of that helmet glass as soon as they detect the spark. So there, because they want to ultimately protect your eyes, so they cannot be like slow and uh, so basically it's depending on the application. It's a medical application or industrial application or consumer application. But I will talk more about UPF. Yeah, but here also, this is also, it's the same thing, which, and this slide, I think I prepared around 10 years back. So basically here you see I have a chip which have an application domain. It's a made up example again. It's a DSP hierarchy, CPU hierarchy, memory, and the power manager. So, and I have a two voltage domains. One is 3 volt and another is 1.5 volt. And you can see 3 volt is, rest of the chip is powered on 3 volt, but only application area is powered on 1.5 volt. Then it's a power switch is sitting here. Power switch is an analog block which have a digital input called, for example, on off or switch, that is controlled by power manager. That power manager will will turn on this power unit for certain application. Your CPU will get turned on. When your CPU is not turned on, this isolation cells will kicks in, and the isolation cells you can see powered up by this red color wire, which is always on wire. So whenever domain is off, still this red color wire, which is always on, will hold this isolation values. So you know what is really going out. And again, you can see whatever coming out of this CPU domain, which is 1.5 volt. You have to again electrically correct that. So it has to go through the level shifter, which is low to high level shifter. So it will translate 1.5 volt to 3 volt. And you can see this signal, for example, I don't know, it's retention control. Yeah, as I said, like it's 10 years back, so I don't have this. So it's a retention control, which is coming from 3 volt domain and going into 1.5 voltage domain. It's going from, again, level shifter, and it's going from high to low. So basically 3 volt is getting translated into 1.5 volt. And again, nobody use actually now retention cells. Some people still use it. So retention cells is like some complex flip-flop which have 2 supplies. One is like switchable supply which you can switch off, and another is always on supply which you see in red color. So when this pink color supply will be off, the retention logic, the logic value will be retained by this red color supply here. Most of the times now, you don't see isolation cells as the standalone cells. You see isolation cells as integrated into level shifter. But isolation cells are, those are not special cells, to be honest. You can just say like it's an AND gate, basically, because AND gate have only one controlling input. So if you have an AND gate, and if it is powered on, and if you control the isolation value, OR gate, and if you control the controlling input to a 1, irrespective of whatever other input is, your output of OR gate is always going to be a 1. So there is no question that corrupting your output. You understand what I exactly mean here? Isolation cell is basically no matter what, even though power domain is off, your output is at known state. So that could be logic 1 or logic 0, but it should not be unknown state.
Hello.
Yeah.
Sorry to interrupt you.
Yeah.
Could we take a break of 5 minutes, because we have started
Yeah,
at
sure.
6. Okay. First session is actually over at 7:30. Okay.
Yeah.
We may take a break of 5 minutes. Okay. Before that, I just request participant to ask any questions if you have.
Yeah, I'm more or less in the middle, so it's fine. Yeah, if you have any question, please shoot.
I have unmute all the participants. If you are interested, you can unmute and have a question with the speaker.
Yeah, I really actually try to make it so that it should not keep, I mean, it will not be 100% crystal clear to you, but I just want, my objective is like you should get fair understanding, like how data is moving from one step to another step.
Okay. I'm just looking in perspective of the faculty member, researchers, and students, basically. So,
Yeah.
what are the different skills that should be gained by the students, okay, or the researchers, so that they will be industry ready? Okay. So, can you suggest the different skills that could be gained by the researchers or the students?
Yeah, the researchers and from students' point of view, or in general, what I say, you have, as I said, like don't let the tool think for you. You
Okay.
think for the tool. So basically, you try to build your knowledge from the bottom of fashion. So as I said, like if you even know ASIC design process is fully automated process, basically by EDA tools. But you should know like what you are inputting EDA tool, why you are inputting EDA tool. Basically, you start from the beginning. Like for example, if I look at this EDA, for example, this topology, this inverter. If I have to simulate this inverter on the paper, you will write all type of equations, more than one, possibly more than 2 equations, linear, non-linear equations, where you will model this pull up path, pull down path, and you will come up with the conclusion like how this inverter is working. Same information is basically you want to simulate, but in digital design, you have more gates. They are in terms of, if not millions, in thousands. You can do this spice level simulation for 1 gate, but you cannot do it for like 50,000 gates which are connected. So what they are doing here AC analysis, DC analysis, whatever you do on paper. And same information they are putting into tabular form, into .lib. So this is nothing but whatever you are going to do on paper, but for sake of EDA tool, it is represented in a tabular format. after in second session, I will show you how that information is actually processed by EDA tool. Because if EDA tool has to invest time calculating this pull-up equation and pull-down equation and analyzing everything, it will take ages for tool to simulate only one AND gate. And I'm pretty sure if you simulate that AND gate in SPICE, it can easily take 20 minutes to 30 minutes in SPICE, real transistor level simulation. What we are doing, we are moving from transistor level simulation to the gate level simulation. But how we are moving from transistor level simulation to gate level simulation? With the help of this database. So basically now we think about, we think at transistor level for once we build this file, and now onward we will think from gate point of view to speed up things. It's the same applies to any analog topology also. If you have a voltage regulator here, or let's say voltage regulator, or for that, okay, voltage regulator is a power block. But if I take, let's say, any module, let's say amplifier. If I have an amplifier in a given topology, I have an input and output. So I need a timing information. How if my input looks like, let's say, input is always comes in terms of transition. It's a transition from high to low or low to high or real-time analog signal. So how my output will look like. So that's the functional description, and how much time it takes to reflect on that input. That's the timing information, and how much power I'm taking. So when I apply 1 here, my capacitance get discharged, and how much power I utilize. When I apply 0 here, how much time it takes to charge, how much current it takes to charge this capacitor. And this I have written. So basically you are leveling up. So just think like you are elevating from transistor level to a gate level. And this is just for sake of calculation. And that's why I will tell you how the accuracy play here role in second session. Because what delay you are getting here at gate level simulation, and what delay you are getting at transistor level simulation will not be exactly same, because gate level delay is approximation taken by lookup table. Because transistor level simulation, you have an exact transition, input transition, let's say 1 millisecond. You have exact load, let's say 1 picofarad. You have 1 millisecond transition, 1 picofarad load. You know the width and length of this transistor. You are performing AC analysis, DC analysis. You have exact time, what delay it takes from input to output. But if you go to the gate level have a lookup table. You see, you give me 1 millisecond, but in my lookup table, I have a lookup table built of, let's say 0.5 millisecond, then 2 millisecond, then 3 millisecond, but I don't have 1 millisecond in my lookup table. Then their statistics will play a role, because I have information about how it behaves for 0.5 millisecond delay and 2 millisecond delay. And let's say I don't have an exact lookup table where I have 1 picofarad capacitance. Let's say I have a load of 0.5 picofarad or 2 picofarad. So basically I'm within table, but I'm not exactly on that row. Then it will do some interpolation. Then it will say, based on this knowledge, I will say the delay for 1 millisecond input transition and 1 picofarad roll delay will be, let's say, 0.2 nanosecond. But same transistor level simulation will tell you, no, delay is not actually 0.2 nanosecond. It's, to be precise, 0.25 nanosecond. So you still lose some accuracy here. And why you lose accuracy? Because you don't have information like what is a parasitic capacitance of this. But there are two methods. Over the in next level, you will get gate, but you will not only get, you will get the parasitic file also. That parasitic file will give you the parasitic capacitances. Now tool will be a more smart. So tool will use this lookup table for your input transition and load capacitance and the capacitance. And then this time tool will say like delay is not actually 2 nanosecond, it's 2.2 nanosecond. And the transistor actual SPICE simulation will say 2.5 nanosecond. Then you will go one level up, then you will get exact topology. Then it will improve little bit more. Sometimes you fall in this lookup table, sometimes you go completely out of this lookup table, and that time it will do the extrapolation. So basically, this is all trickery, is a mathematical. But try to understand here, you're moving from transistor level to the gate level for sake of simulation time. Or not simulation time only, but the speed up, whole speed up process. And again, to lay out this chip, you cannot handcraft each transistor, because they crafted this manually. They lay out this inverter by hand, and they perform all possible human optimizations. So how close they can be, how should be the VDD net, how should be the ground net, and how compact it should be, how much compact I can make it possible so that it is manufacturable. So again, take a note that I'm talking about manufacturability. So once you get that structure, that they will put that information into the left format. So the tools which are working in this level, in this ladder, they don't really need to think at transistor level. They just need to think about block level. And that's why I said, like, this ASIC design is a kind of a cocktail of computer science and the circuit design. Because here you're talking about circuit design, all AC analysis, DC analysis. You are compiling all this information of AC analysis, DC analysis in some kind of a library. That library is going to the EDA tool, and that EDA tool acts as a computer program. And you, as a user of that EDA tool, again act as a computer programmer. Many people don't like it, think like ASIC design is not really a circuit design. Circuit design is like more, you design these standard cells, you design inverters, AND gates, memories, you design op amps, oscillators, regulators, low noise amplifiers. So this is actually circuit design. This is one level up. I hope I answered. By the way, what was the question? Maybe I completely lost.
The question is in terms of means we have to make industry ready, either faculty or the students.
Oh, yeah, yeah. So basically, when I talk about this one, once you make your base strong, you start understanding file formats, you understanding everything. So basically here you have again a good foundation. Then you start learning actually these specific methodology. Not again, I'm talking about tool, because you consider this synthesis as a methodology. What I am doing here, my job doesn't matter which tool it is doing. My job is like, I have inputs, I have outputs, I have functionality sitting in the middle of inputs and outputs. So my job is to tell tool like what my output port is going to drive. It's going to, let's say it's connected to a display, but you have to tell in terms of capacitance, like what is load. I look here so that it choose a cell with that drive that output port strong enough. If you know what is input look like, if your inputs are some kind of sensor inputs, then you know like what is input transition look like, what is your limitations, then you know what type of input pad you have to use. So basically, if your input is coming from sensor which is only 1 nanoampere current, for example, and then that goes through a low noise amplifier, then it goes into amplifier and amplified, and then that goes into some kind of a reasonable good level, and then you know that this is my operating level. So you have to understand RTL coding. After RTL coding, you have to understand, if you want to just think from synthesis point of view, you have to understand synthesis as a process. Try to be tool independent. Think about that. If you don't have access to design compiler, you can use Yosos, which is open source. Once you have a gate level netlist, you have these models from the open source library. You can perform gate level simulation. If you can perform gate level simulation with open source tool, you can perform gate level simulation tool from any industry standard tool. So just build up using open source tool. And these are even quite this is quite a good environment for faculty. The one who wants to get really expertise between processor design, where you want full control, like on the architecture compiler, because this is not generating only architecture, it is generating compiler for you. So you can look into, like, based on this architecture, how compiler is written, how the compiler doing cross compiling basically. So this act as a sandbox, as I told you, like basically this is a really a good sandbox. Personally, I really like it. This one machine learning thing, which is hot topic, this is a one-time process. Once you know, like how the neural network looks like, what training exactly means. Training is a process of giving many inputs. To begin with, you start with random weights. You do these iterations many times. More iterations will do. That is a training time. More good weights you will settle on. More good weights you will settle on. You have a trained model. Once you have trained model, it's your choice. Either you go hardware way, you will go software way, and you have all things available open source, because no one can prepare 70,000 images on their own, to be honest, to 728 pixel by pixel, 728 by 28 pixel size. So basically all raw material is available for you. So for faculty also, I mean, just I will say jump in. So it's a really good jump start here. I mean, so far there should not be any showstopper. What you need is only Ubuntu, because I think some tools they run only on Linux. I know this can work on probably Windows, but many tools they work on Linux. So you need a Ubuntu kernel, and you're free. So far what I have shown is this is a technology independent up to this part. You don't need any technology here. Technology starts kicking here. You have open source PDK, open source tool. Yeah, so basically this is good start, and it's not I'm just presenting. I'm using Yosos here, for example. I have never used this the one which what was that? There are a couple of tools. For example, when I come across, for example, Danish Technical University here locally, they are actually working on this open source tools, and their clear motivation is basically want to do everything without commercial software. And this is basically a place where they have actually, I will show you in next slides. I have that also. Open source RTL to GDS.
Okay, sir. Thank you. Now you can continue with your.
We can take a
flow.
break, 1 minute maybe.
No issues. Okay, you can take a break up to 3 minutes or so.
I will be back shortly. I will just
Okay.
be
Okay,
back.
no
I'll
problem.
just tell my son to. Yeah, bye.
We will join in maybe 2-3 minutes. Meanwhile, if participants have any questions, please put in the chat box or you can unmute.
Yeah, hi, I'm back.
Okay. Okay, sir.
I think I was pretty slow, but I think I'm still halfway done. So I don't think so. Time is really a problem. We will finish it on time.
Now you can continue with your flow. Okay, no problem.
Yeah. But in meantime, if you have any question, just ask. It's no problem. So basically, you can see you use along with the functional information, you started giving power information also in coding style, and that too upfront, because you can simulate this in your simulation. So if something which is doing electrically wrong, if for example, if you're trying to access register which is in power domain, which is turned off, so it will give you uh, basically X. In real life you don't get X, but it will in simulation, you see you're trying to do something crazy. So I just want to give you a quick glimpse how to look like. For example, this is a standard cadence tool called Exilium, and probably you know the design browser, how it looks like. It shows you the top level design, and then the instances or hierarchies below that design. But here I'm intentionally showing power structure of the chip. So this is a chip. It's called digital core. It has a one instance called SPI controller, for example. And SPI controller only the candidate which have its own power domain. And you can see this bulb is not, okay, I'm not sharing. Can you see now? Okay, so you see digital core and SPI core. It has a two power domains. One is top power domain, which is in purple color, and one in gray color, which is the SPI power domain. So this is how it looks like in the tool. And you can see it visually also. And you can see this bulb is not glowing. So that's the power domain is off. You can see all these candidates which are red. So basically tool is saying like there is no power, and that's why they are red. And if I perform, and now you can see along with this inputs and outputs, you can see the power nets also in simulation. So you can see your supply nets, and you can see here what is the state of this power nets. So these are not functional nets. These are the power nets, and these are basically telling you VP SPI power is off, VDD 18 is full on. This is 1.8 volt. You cannot see. VSS is on. VSS is ground, so it's hold to the 0. And this is how the power hierarchy look like. So this can give you kind of visualize feeling that whether what you're writing in Power model, it really adding up what you have in your head. So now we will move to a timing constraint. So, and now as I start, as I said, like just before break, like try to be a tool independent or think as a tool independent. So doesn't matter which chip you're doing. What you need is like you need a clock, obviously. You need I mean, basically you have to timing constraint. So basically you're telling the tool that how the off-chip environment look like with your chip is going to communicate with. So here I'm saying like this is my blue chip. It's going to receive clock. If I'm using this clock and internally generating some clocks, let's say divide by 2, divide by 4, whatever. So now I have to tell that I'm going to generate if I have any generated clock inside using this clock. Of course, no clock source is ideal clock source. So every clock source have some kind of uncertainty. So you will tell like even if you're aiming for let's say 5 megahertz, you have uncertainty of let's say 0.1 nanosecond. The edges of the clock will drift 1 nanosecond too early or late. Clock latency, so what time it will take from the clock pin on the top of the chip to the clock pin inside the flip-flop inside chips. So that's basically a latency, network latency. So there are actually two parts of latency. They want to model for some reason latency from the off-chip clock source to the pin of the chip. They call it as a network latency. People normally don't show because most of the times clock generator is sitting inside chip as well. It could be a PLL along with oscillator and something, but sometimes you do get clock from outside, so you have to model. Then how my output delays look like. So basically, I will just mute this. Yeah. So how you will of course put this chip on some PCB in future when you will get the chip. So you have to reserve some delay, because if we keep this motivation in your mind, data move from one flop to another flop in one clock cycle. So if there is a flip-flop sitting here, and if it launch a data, it should get captured by off-chip device on next clock cycle. So basically data should move from this flop to this capture device in one clock cycles. And you have to reserve some data delay so that you can perform this PCB level, what you call layouts, and also this off-chip device have some requirement. It also needs some time to settle. So basically you reserve some time output delay. Similarly, you reserve some time for inputs. So whenever off-chip device try to communicate to a chip, it will tell like, I will give you data, but I need some time to put data on this pin with reference to the clock age. Input transition. So how strong my input transition or input signal is. If my input signal is weak, so of course I need fast cells with low VT, which can trigger on those weak input transitions. Output load, what is the load I'm going to drive these pads. A timing exception. So that means even though if we see this more default assumption that data move from one flop to next flop in one clock cycle, there are some paths in your design. Those could be multi-cycle or false path. You really don't bother like how much time it takes. So basically you tell tool like, I have a certain path. For example, if you're accessing memory, memory is relatively slow compared to your clock. So obviously you need more clock cycles. So you tell the tool like, it will take 2 clock cycles. So don't perform timing checks on every clock cycle. Perform on every second clock cycle and complain if you see the problem. So that's we call multi-cycle path. Sometimes we are communicating or connected to an analog block, it really don't bother about timing. And that time we see like, okay, this flip-flop is going to connect it to some kind of, let's say, power switch. And I really don't really bother about how fast it is going to power switch. So I mark as a false path. Basically, you're telling tool like, don't waste your energy optimizing these paths, because those are not really timing critical. So that tool use its effort on the design, on the part of the design which is timing critical. So this is the only information you will pass, and you're done with this so-called timing constraint in your design. So your synthesis tool now know what external environment look like and what chip it should synthesize. Now verification. So once you have the chip synthesized, you not on at chip level but at RTL level also, you think always about verification. One traditional way of verification that you get a design, you write some tests. Of course, design is, for example, let's say VHDL or Verilog, you write test also VHDL in Verilog, and it will wiggle those pins, put the stimuli, and it will check your hardware or your design under test that is behaving properly. This is very slow, time consuming process, traditional process. It has very low adaptability. That means you have to write individual test cases for all type of scenarios. So I will show you with one example also in next slide. And your coverage is also not so good because you have a human limitations, like how many test cases you will write and then how many test cases you will maintain. So it's taking long time. Earlier in ASIC design team, there was a proportion like number of designers and number of verification engineers were same. Now there is no. Okay, from career point of view, again, your question, Yuvraj. Now you always starts with some either verification engineer or design engineer or static timing analysis engineer, but over the period you do everything. So basically, a designer in the first phase of the project, you are a designer. In second middle phase of the project, you are verification engineer. In the low end of the project, you are basically timing closure implementation guy. But that comes over the period. It's not you start these things out of university. You always starts with one domain. So the industry standard approach for verification is UVM. So UVM is basically you try to use this UVM base classes, and the UVM base classes will give you a base class where you can write your own class. So you can generate UVM models for SPI, UART, I2C, or your custom blocks for that matter. So what you will do, you will write basically a system Verilog, which is pretty close to C, but I will still call it system Verilog to be precise. So you will write classes which can perform some activity. So basically, instead of if you are performing a test on SPI, so instead of putting slave select, writing SPI input data, everything, you will just say by one class function like, okay, write value 01 on this SPI interface. Then that will go to the driver. Driver, no, this is basically driver is designed in such a way that it will respect the SPI protocol and it will put the stimuli on SPI interface. And how exactly it look like? This is the base class. Basically, you have a UVM base classes for driver, sequencer, monitor, agent, scoreboard, environment. You build this environment for yourself. You do it once for this SPI UART for standard interfaces at least. For custom interfaces, you do develop your own. For example, PCD, which is a proximity coupling device, which is basically NFC protocol. which is basically sitting in your credit cards or contactless cards, which goes into the magnetic field charge it, then it's modulate magnetic field, and then it perform the data transfer over that magnetic field, and same magnetic field act as a power source. So for that, there you have a coil 1 and coil 2 as an interface. So basically you can write a UVM model which can drive that coil 1 and coil 2 modulation, and then you can perform all the tests. But that will give you basically one-time investment. You write this UVM component one time, and then you can reuse many times. So this is one-time investment. So this is actually something which I did from scratch in Presto, because they were not using UVM in the beginning, 10 years back I'm talking about. So this is again something not any proprietary. This is again, standard driven by Accelera, and you can download, or you can see this PDF, and you can see the real motivation why not this traditional test bench, and why this system Verilog test bench, how these base classes will give you one leg up, and how you can write these test cases using these components, so that you can generate any kind of environment, simulation environment. It's like as flexible and as close as like you have a chip on a board, and you have some real life SPI component you connected to that chip, and you are controlling this by computer. So basically you have complete freedom. So it's very close to reality. This is the base class, how it looks like. So basically driver you will derive from UVM driver, sequencer you will derive from sequencer, monitor will derive from monitor, and blah. This you can make a closer look. This is another area where faculty or the guys who are latest out from university can really building their competence. This is also good start in industry to enter into, if you can start your own UVM components. Basically, what I did, our motivation was to start verification early. So not to wait till design is ready. So verification should start early. And how it can start early? So upfront, if you know like you're going to use SPI in your design, if this design is going to use SPI protocol, and you know SPI has a master and slave. So why wait till this design is completely ready? So what people do, or what this is a methodology which we developed. So basically you start writing your SPI component, standalone component, SPI environment. And that environment should be configurable. So basically you are configuring that SPI as a master or as a slave. When you write with this, writing this environment, so basically when you write standalone SPI, its own subscriber, its own monitor, its own driver, its own, it's not subscriber, it's subscriber, and it should be monitor, subscriber, and its agent, and what it is. This is a typo. I think I have to look into that one. The subscriber is sitting here. No, sorry, this is subscriber and this is scoreboard. But I can show you the real. So I'm sorry for this. This is the no, UVM agent scoreboard and sorry. So this is a sequencer. So what sequencer does, like whatever you are going to call function, that goes to the sequencer. Sequencer tell driver, I have something new for you, and these are the C classes. So this function will call something, some function here. That function will call this function here. This function will say like, okay, I have something new to put in this interface. It will put on this interface. When it's done, it will tell that subscriber, I'm done with your sequence, so I'm ready for next one if you have. The monitor will keep monitoring this interface so that you're respecting SPI protocol. So if you don't respect SPI protocol, the monitor will complain. So that's how we will write SPI. The same SPI we will write such a way that you can configure it as a slave and master. Then you will create your own top level environment where you instantiate that SPI. 2 instances. In one instance, you will configure as a master, and another instance you will configure it as a slave. So basically, this master is talking to slave, and then you will write a test case. So basically, you are verifying your UVM component. It's doing the job of SPI. Once you ready with this your UVM component, you are one step ahead. So when actual design will be ready. For example, if your design has a SPI slave, so you will delete this, or you will remove this SPI slave environment, and you will instantiate actual design here. And then you will run the test case. So basically, you start writing your test cases or as much as you possible before your design is ready. So this is one of the methodology we follow. So basically, you can write your UVM component. You can begin with the SPI because it comes with the flavor of master and slave. So you can write a generic component which can be configured as a master and can be configured as a slave. Then you instantiate same component 2 times. One in first instance you configure as a master, second instance configure as a slave, connect them, and start communicating. If you can communicate, that means you have 2 components ready. Basically, you have verification component ready, which you can use immediately after your design is ready. That's basically give quite a boost in your design cycle. Now, again, I'm talking about why the verification methodology, because as I said, like if you start thinking from the traditional verification point of view, then how many test cases you will write to perform this communication? Maximum what you will do, you will write one test case where you will give some, like for example 10 bytes, and you will try to write 10 bytes and you will try to read 10 bytes. That's all, most likely. Or you can write, if your FIFO is let's say only of a depth 8, you will try to write 8 bytes and try to see if the FIFO is behaving correctly. That means it's when FIFO is full, it's overrun. Or you will try to read the elements from the FIFO when the FIFO is empty, and you try to expect its underrun is triggered. But everything this can be done by only one test case. For example, if you write one test case, you can use let's say a random burst size, and that random burst size could be from 8 bytes to 64 bytes. So it can, every time you will run that test case, it will randomly pick the size of the data. It will not only pick the size of data, it will pick what data you want to transfer. So not necessarily you are transferring every time 01, 02, 03. You can randomize that data too. So you can randomize size of data, you can randomize data itself, and then you can perform this read and write operation. So basically, you are trying to simulate real life scenario. Then you will perform some corner test cases. So what you will do protocol distortion. Protocol distortion means like you will try to trigger that slave select before your frame is complete. And you want to make sure this SPI block is not going into some unknown lock state because you are distorting the frame. Because then if you want to come out of that lock state, you have to reset the chip. And we don't afford that. Every time you don't need to reset, you cannot afford resetting chip every time. So basically, your code should be robust enough so that it can respect protocol, but it can handle the protocol distortion. You can try to mimic. You can have a UVM component that mimic as a system interface. So you can try to read these FIFOs, and you can try to read in certain corner cases, like read when there is no data available. So it should trigger underrun. You just keep filling FIFO, you should trigger overrun. Or you can do extreme corner case, for example, because what is happening here when your SPI transaction is coming, it's placing data. For example, if we're talking about this, this one is let's say receive FIFO and another is transmit FIFO. So let's say if we are talking about transmit FIFO, So when SPI is reading, when SPI transaction is coming, SPI putting that data into transmit FIFO. And when system side is reading that FIFO, it's reducing that FIFO by 1 because when system reading. And then there is a, let's say, a FIFO pointer, which is pointing to an element, which is the latest element we should read. Or or a pointer which is basically telling you how many elements you have in that FIFO. So you have to mimic exact scenario. What will happen? Exact same point where you have a new data coming from this. So again, I'm not in exact time when my SPI transaction is coming, and that is putting new element in this FIFO. And at that exactly same moment, I'm reading from system interface. So what this pointer will behave? Will that pointer move up, move down, or will be unchanged? So this is the extreme corner case. And this is basically a corner case or example I have developed because this problem we've been through some time back. Not recently, many years back. Because the FIFO here, it should always get increment when there is a new SPI transaction is coming. And the FIFO pointer will decrement when system interface is taking out element from this FIFO. And the chip perform exactly weird because this happen. It's not very likely, but though it's unlikely, it can happen. So you are exactly writing and system interface is exactly reading and your FIFO pointer should be unchanged. So the objective is to get full functional verification, get robustness of the design, and make sure that your design is not going into unknown state or lock state, so that it stops accepting, it stop functioning completely. And only way to come out of that unknown state is a hard reset, which we don't want to do. So this is actually how the interface look like. This is exactly same environment, the one which I have shown. And here you can see, just pay attention on this top level environment. So I have a top level environment where I have test. Then I have a two verification component. One is base PCD. Basically, this is NFC and SPI. And then if I break down this SPI, you see it has a driver, monitor, sequencer, and subscriber. And that's what I said here. I made a mistake here. This is sequencer. And then when you will run any test case, so test case is always sitting here, UVM test case. It will put something on sequencer. Sequencer will give it to driver. Driver give it to agent. From agent, it will be placed on the interface. Interface is somewhere here. I have to expand this. I forget to expand this. And then that's how it will go to the chip, and then chip will simulate. So after this kind of simulation, you write these test cases. As I said, like you write random test cases. So basically, you're not writing only one test case. You write a test case such that it can transfer burst of data of any size of 8, even though let's say your standard size is 8, 16, 32, but you can still try to see the burst size of a 9 and see how this SPI behaves, because you don't know how off-chip element will behave in reality, in real life. So you have to just make sure that your SPI is robust enough. So when you will run these random test cases, let's say 100 times, you basically run oops. Yeah, you will run this 100 times, and then you get a kind of a database because you gave 100 different inputs or bursts, and then it can give you a matrix called a coverage matrix. And that time it will give you code coverage, which is block, branch, expression, toggle, FSM coverage if you have FSM stands for finite state machine. So, and it has a many states. So how you are making transitions from one state to another state. So it should cover, you should cover all possible transitions in your test. And then functional coverage. So basically you will write assertions like what you expect inside design, and all assertions will get triggered, or should get triggered, not will, should. And after running this test cases, let's say 100 times, random test cases, it will give you kind of coverage metrics. So it will tell you this is your design. Look from here onward. So this is chip instance, and from here onward you see not so great coverage because I have collected coverage from only one test cases to just show you. And then you can see for digital core, again, analog core here is a just behavioral model. So I'm focusing only on digital core. So for digital core, you can see I have a code coverage which have a block statement expression, and there it can show me for this only one sequence I have poor coverage. So that means something which is not covered, I can double click here, and then it can basically tell me like what corner, what scenario I'm not covered in my test environment, and that one we should cover in order to make good test coverage. So now that's all for design and verification. I will go to the synthesis part. So synthesis, this is again the standard flow chart, which probably you have seen many times. You pass some inputs. Inputs could be the RTL code, the .lib library. Now I told you, now you stop thinking at transistor level, just think at gate level, because you are leveled up, you are elevated from transistor to gates. And now you get this information in libs and lefts. You have design constants, which I told, timing constants. This is basically how off-chip environment look like. Power environment. So what is the supply and blah, blah, blah. The floor plan, if you want to perform physical synthesis, physical aware synthesis. So tool knows roughly like how long one flip-flop is from other flip-flop. And what it generates for you is a netlist, synthesized netlist, SDC file, UPF, test protocol, if you insert test here, and guidance file. Guidance file is basically a synthesis will tell you what kind of optimization it's performing, whether it's data optimization it is performing, clock optimization it is performing. If there is any dead logic, it's trying to remove that dead logic. If there are hanging pins inside your design which are not used, so it will basically fix those hanging pins. Of course, it will warn you. I will show you the report. I should. Yeah, okay. So this is how the synthesis script look like. Again, I'm repeating, no more transistor level, only at gate level. So you read the library, you read the RTL, the design. Forget about this. It's just to speed up simulation because these tools can allow you to use more than one core. You provide this timing information in the form of multi-mode, multi-corner. Multi-mode, multi-corner is basically the library which you will get here is not, you will get in different flavors. So this library, because even though we fabricate one transistor on a die, the transistor which you fabricate in coordinate, let's say die coordinate 0, 0, is not exactly same as you fabricate same transistor at die coordinate 100, 100. The transistor width and length, they will still little bit vary. So basically, it will give you a kind of a lib file in 3 scenarios. One is like typical scenario. So very likely transistor will look like typical. A slow scenario where the transistor speed will degrade because of the process variability, because there is lots of variability in a process. And sometimes the process variability can help you, so that can make your transistor fast. So it will give you this lib file in 3 flavors: slow, typical, and fast. So here you will make multi-mode, multi-corner. So you will give 3 dot libs, how it looks like when it's slow, how gates behave when they are slow, how gates behave most likely, that is typical, and how standard cells behaves when they are fast. And this variation appears because of the process variability. Then there is a parasitic information which I told you. That is about that is a capacitance table. So all the wires which you will see, they will basically, capacitance table will be a lookup table again here. They will tell you the width of the wire and the distance between 2 wires, and then it will create a lookup table for this. Based on the distance between 2 wires and the width of 2 wires, we have some capacitance values. And then timing information, not timing information, this is actually physical information. This is a typo. This is physical information. Timing information is here itself. So this goes to the tool. And you read your design. And when you read your design, you elaborate the design. When you elaborate, that means you just build the inside data structure. So basically you have all gates, you can reference to all gates. So basically you have the description of all gates. And if you don't have any description, then that will be marked as a block box. So tool will say like, I see some kind of a design element here, but I don't have any timing functional information whatsoever about that block. So basically you will build the database, and then you will, this is optional, you will read the floor plan. So floor plan means you will tell the synthesis tool mostly what is the width and what is length of the chip, so that it can imagine and build a statistical scenario like how far away these flip-flops and combinational cells will be and how timing paths will look like. And then you will initialize design. So basically, this is the super command. I'm talking from Cadence tool point of view, but think tool independent. Open source tool, Yosos does exactly same. Though command is not literally same, but the fundamentals are unchanged. So the fundamentals are here: design, reading your design, reading your library, and basically adding things up. So nothing is a black box, or if there is any black box, you know why it is a black box. And here you initialize the timing constraints. So here we are talking about test. So when your chip will be there, basically all the flip-flops, they will get stitched together in a scan chain that will look like a shift register. And basically we are telling like, now don't bother about the functionality. So bother about how test should look like. So that means which pin will act as a scan clock. So that shift register will have a clock. So who will be that clock? Your design will have some kind of analog cells, some block which you want to be put in some kind of known state when you're in test mode. So you have a test mode. So you say like, okay, if I have memory, I don't want to, or let's say if you have an oscillator or memory or A to D converter, you want to tell like, don't let this analog blocks to meddle in my digital test process, because those are analog blocks, and I don't want they to interfere in the scan testing. So I want to hold their inputs and outputs to the known, basically outputs to the known state. And then shift enable. So the pin which I will show you. So basically, which pin will configure all this shift register into shift mode. So that means you can shift whatever data you want to shift inside that shift register, and meaning that inside all those D flip-flops inside your design, to get known state in all D flip-flops in your design for test purpose. I will tell you why for that, what is for that. And then you define those scan chains. So basically you will define like what is scan input and what is scan output, how many scan chains you want to see. And you will basically configure that, and you will check for DFT rules. DFT rules, basically the tester which is going to control your test clock, test scan enable, and the test mode pin need to control all scan elements, basically all flip-flops. There should not be a software reset or flip-flop which you can reset. You can reset only by writing some flip-flop. So here tool need a full control to a clock pins and reset pins of your flip-flop from the here. So if I have this as a scan input, and if let's say this is scan enable and this is reset, scan reset. So if I control this pin, all flip-flops inside core should get reset. If I cannot control that, scan chain will the tool will complain, because tool will say like I need to bring all these tools to the known state for my sake to build the test patterns, because this is my starting point. So that is basically DFT structure, and you will again check design for unresolved instances. So basically here you should not see any unexpected unresolved instance. If there is unresolved instance, then you should go back and check something is missing, reading maybe library is missing or something. And if it is expected black box, then you can live with that. And that expected black box must be a custom block. It could be an analog block where you don't have library model or timing model. But ideal scenario, you don't get any black box here. And if you get and you know that, then you can live with that. You basically give this Innovus path. This is again just for sake of cadence tool. Don't really take like this is too specific to cadence. For open source tool, it should be same, but maybe open source tools, they are not physical aware. So you don't need to provide place and route tool. But here I need to, because it need to use these features of physical aware. And then here it performs these 3 powerful commands. And here the question which you asked before. So what's the trade-off of power, area, and timing? So this tool is by default is configured as a effort level medium. So that means timing effort is medium, area effort is medium, and power effort is medium. If you have a certain choice, you can change that order. So if you want like ultra low power, so you can say power effort should be high. And here it will perform actual synthesis using 3 commands. This sym generic will perform actual synthesis, so where your RTL code will break down into logic gates, D flip-flops, ANDs, ORs, technology independent again. So up to this, it's not using any technology. Then synth map, so those technology independent gates, it will map to a technology cell from the .lib you are providing here. .lib you are providing here. And then it will connect scan chains. So basically what it will do, it will take all outputs of the flip-flop and it will connect to the scan inputs. So this is scan insertion. You see, this is without scan insertion. So there are only 2 flip-flops. There is some combinational logic. This is actual data path. So you can say this is actually functionality. And what it is doing here, when you insert scan, it says like, tell me what is scan input, tell me what is scan clock, tell me what is test mode. And then I will take the flip-flop and then I will take the Q pin of that flop and will connect that Q pin directly, not through combinational logic, because that will be controlled by scan enable. Scan enable will bypass combinational logic and will directly give a feed through path. So it's just a wire connecting from Q to SI pin, so that it will become a shift register of a depth 2. So one flop in shift register, second flop in shift register. You have a scan clock, you have a scan input, you have a scan reset, you have a test mode. Using this scan clock and scan input, you have a possibility to feed in 0, 0, 1, 1, 1, 0, 0, 1, whatever you want. So that you can force this flip-flops, at least, not this combinational logic, this flip-flops into known state. I will tell you why this, but just keep this in mind. This is for test pattern generation. And this acts as a shift register. And then it will basically perform synthesis and then will write kind of reports. This is Cadence family tool. So Cadence will generate kind of intermediate database, which you can directly read into their physical synthesis tool. So don't bother about this. If you're using another tool, then you will not get this, but you can again live with this standard command. So you can output synthesize netlist, SDC, def file, test protocol. Test protocol is basically, test protocol is telling me what is scan inputs, what is scan clock, what is scan reset, and how the scan activity is working. And then you can write scan def. So basically, it's basically telling how the shift register look like. So basically, it's telling like first scan input is connected to U2 register, and U2 register is directly connected to U3 register. So this is scan information. So basically, order of scan chain. I will tell you why this is important, but just for a moment, this order is important. This is the first flip-flop in the shift register. This is second flip-flop in the register. And then it will write kind of a model, scan model also. Basically, if this block, scan inserted block, should go into another block, and if it should use this already implemented scan structure, then you have to pass information into this format. So basically, this is the functional information. This is timing information. This is the geography information. This is a scan shift register information. This is test protocol information. And this is a scan structure information. So who is a scan input, scan output, scan clock. If you want to stitch that, integrate that into top level, one level up in another design. So this is how synthesis script will look like, and then it will generate tons of reports. This is the more tooling part, or I will say, you can say why I say it's something in between computer programming and the circuit design. So here you are more like not really computer programmer, but somewhere in between. But you know why you're doing this, what electrical requirement you want to meet here. So that's something circuit part. And after this report, you get kind of this report. So this is more important report of a check design. Here you should not see something alarming, which could be, for example, multi-driven ports. It's alarming. Basically, one net is driven by two different drivers. So you know what will happen in reality. There will be one will be the aggressor, one will be the victim, and you really don't want it. Doesn't make sense in reality. Undriven ports. So basically, if something which is unconnected, it can possible if you have an IP from external vendor, and some part of that IP you really don't want to use it, so you have to tie it to either logic 0, logic 1. Some kind of constants, you have to have some constants, maybe some configuration registers where you have constants. Some hierarchies you want to preserve. That's for sake of verification, because you want to keep design intact. Otherwise, it will flatten out and break down everything into one hierarchy, just flip-flops and the standard cells. But if you want to see in that netlist, okay, this flip-flops and combinational block is SPI, this block is my processor, this block is a finite state machine, then you want to save hierarchy. Of course, when you say save hierarchy, you're basically constraining tool. Then tool cannot perform some cross-boundary optimizations. So so many tool vendors basically try to convince you run tool as much as possible in default mode. Constrain the tool as minimum as possible. Constraint as minimum as possible means not the must-have constraints you have to mention. That means load, input transition, and all those. You cannot rely that because the off-chip environment you know better than anyone else or tool. But the optimizations which to perform all those things, tool know probably better because now tool have all information of the flops and the combinational logic and how they are connected and so tool you can give them like a free hand to tool, but still like listen, but verify. So see what jobs tool is doing here, and if you don't agree with something, go back and change the script accordingly. So this is like a two-step forward, one-step backward approach sometimes, but that's how it is. Then this is a power report. At this, no, clock gating reports. Okay, that time I was talking about here, we are not letting tool to insert clock gate because as I told you, clock gate you can insert in RTL or you can tell tool also to insert clock gate. But if you have a clock gate in RTL and if you tell tool to insert clock gate also, so sometimes it can become like a redundant clock gate. So basically what happened, like if you have this design, you give it to prime time design compiler or Innovus for that matter. And if you say like, this is my design, just synthesize, and then you should say like, I have implemented clock gating, so you don't need to do anything. But if you don't do that, and if you have done this one, and tool, you tell tool, do clock gating. So most likely you probably see, I mean, the tools are becoming more advanced, but you can probably see something weird. You can see a clock gate after clock gate, which is redundant, which you don't want. So in this design, many design groups, they don't want to rely on the tool for clock gating because they know that they're designed better than the tool. So they don't let the tool perform any clock gate. So that's why you see RC clock gating instances 000 because we force tool not to do anything. We have done it in RTL. Then synthesis report. This is a check DFT report. As I told you, it will complain here. If you have something like some reset pin is not controllable, some clock pin of design is not controllable by scan clock, by scan reset, or you have some kind of combinational loops. So it will report you. If you get something, you have to go back, you have to revisit. As I said, like it's an iterative process. Sometimes you have to go back, you have to fix that problem, or if that problem is not genuine, you can ignore that. But most of the tools, most of the teams, they don't really take a chance because there is a term coin in the ASIC world. It's a first time right. So they expect, or many companies expect, to do things first time right, because once you carve everything on the stone, I mean on the silicon, you are basically at the mercy of the software workaround. So you don't want to get into that kind of a critical area where you have to do the workarounds. So basically, so you have to go through these reports, and this can give you kind of great information also, because this is small design. So it can tell you like, this is the scan clock I'm using. You can see it's in this design there is a mixed clock edge is used, positive clock edge and negative clock edge, and that's why you can see it says like, I have introduced one lockup latch because it's using some part of design is toggling on the positive edge, some part of design is toggling on the negative edge, and then it says like, total I have 1,000 registers DFT passed, and yeah, it should add up as 1,002. Is it adding up? 2 and 11. Yeah, it's adding up. So around this 1012 flip-flops, you can see 692 are positive edge trigger. These are negative edge trigger. So this kind of information you get from this report, and then okay, you get this as a power again. Parkareswar asked me about power. So you get power report. Again, this is not power, accurate power. You remember, this is gate level power. All the information about nets and the length of net is missing. But still, it's a kind of a number which you can rely upon. You can see like how far away from your target, how close to your target. So basically, it gives you good starting point. So here you see leakage power. Now, if you suddenly see your leakage power is too big, you don't want to. You don't want to. What? Okay, Kishore. Okay, it's okay. If you cannot afford this leakage power, then you can go back. You can tell tool like try to insert more high VT cells. Then this leakage power will go down. Switching activity, you can't do much because this is, again, it's not very accurate. It's highly inaccurate, I will say, because this is based on statistical switching activity. It's not real switching activity. That means it will say like, I have these nets, somebody draw something, but I don't know how to take it out. So I'm first time using this tool. So do you know how to take it out, this drawing? Or okay, we leave it that. It will be nice if someone can. Okay, it's me or it's. Am I? Can you see this drawing as well? These blue lines? Can someone unmute and tell?
Yes, sir.
You can use
Do you know
Control
how?
Z.
Can I? No, it's not me who is doing that. It's someone else did that.
Yes, yes,
Excellent.
that is annotation, sir. Don't worry, I just disable the annotation.
Okay.
No,
Okay,
he
it's
is
not.
asking about the blue lines which are there on the screen.
Correct, correct. Annotations. I will just somehow.
Okay, leave it that. It's okay. It's not that important. I think it's not really bothering me. So where I am here, synthesis report. Okay, power report. Yeah. So here, for some reason, okay, if you're not really happy with this leakage information, you can go back. You tell tool or constraint tool that use high VT cells because I want to reduce leakage. Or if you switching power, you don't really rely upon this at this level switching power, because this switching power, because it basically did based on heuristic or statistics. Basically, it says like, okay, this cell will toggle, this net will toggle 20 times. This probability of toggling this net is 20%. Probability of toggling this clock net is, let's say, 80%. Probability of toggling this net is maybe 30%. Based on that, it will do that, and it will tell you that which kind of algorithm it's using. There are some algorithms, statistical algorithms. I don't have in-depth knowledge of that one, but this number is not something rely upon. You can give your own switching activity later on, but here what you should pay attention is to mostly leakage and internal. Internal power is basically when switching happens, both the pull up and pull down transistors, they will be on for a short time. These two transistors. So when switching happens, when this C pin will go from low to high or high to low, this PMOS and NMOS will be high, and then current will drive from this VDD to ground for short time. So you can improve that if you have some kind of good cells in your library. Then this is again timing. So I have just shown you one example as a timing. So you can see what tool is telling, like after synthesis, it sees like one clock gate. Clock gate is controlled by this register, and it says like the clock is coming. Let's say it's basically in this timing report. You can go through timing report whenever you have slide if you want. But what it's saying, like you can see the latencies are like it's in picoseconds. So you can say it's 4 nanoseconds and 4 nanoseconds latency. So this is basically how I am modeling as a synthesis guy. Like I expect like when I will get real chip, when I will put clock on the primary clock input, it will go to the C pin of the clock in 4 nanoseconds. So basically, I'm giving room to a tool like if you want to optimize clock network, optimize such way that it should not be more than 4 nanoseconds. And the clock gating check, what it's telling me, like here it's your free running clock. And when you are enabling this clock gate, which is B pin of this gate, so basically you're driving it to 1. So the controlling pin will be the not B pin, but the A pin, which I have not drawn here. Let's say this is A pin, the one which I have not drawn. So the A pin will be the controlling pin, which is the clock pin, and the clock will propagate to a Y pin. So how you want to propagate it? So you want to enable that clock gate such that when the clock is low, so that next clock, the propagation will start. It will be the clean clock propagation you see here, the Y pin. You don't see the distortion. Distortion in the sense, what will happen if the B pin go high somewhere in the middle here, where my cursor is. I should have drawn this figure. But if my B pin goes high somewhere here, I get a clock out, which is basically a kind of a small pulse width here, basically distorted version. And that can create a problem for a timing through to the design, which is after this Y pin. So this is a clock gating check. So what it is checking, like I'm disabling and enabling clock gate in good time without distorting clock. So you can see here, so this rising edge coming at 504 nanosecond. This clock edge, next clock edge coming at 525.6 nanosecond. And my clock gate should appear not here, neither here in this range, nor in this range. It should appear on this falling, after this falling edge, but before that rising edge. So anywhere in this timing window. So that's why you see this flip-flop is negative edge trigger. So this Q pin will change only after this falling edge, before that rising edge. So this is the sweet spot where you can turn on the clock gate without distorting your clock network. I hope you understand that. It's pretty straightforward. And if it doesn't change, if it change here, I will get violation here. So tool will tell me you're trying to control clock gate, but the setup check is violated because your B pin is changing after 525.6 nanosecond. And basically indirectly tool is telling me then your Y pin will not be ideal clock. It will be a clock something which is starting like this, and then some small pulse, and then after that normal clock. So only first pulse will be the shrinked, but that shrinked pulse can create problem, and that can be a disaster actually, because it can create a timing violation, and then basically every time you will toggle this clock gate, you are bound to create noise. A noise in the sense error in your functionality, not noise like a electrical noise or something. Similarly, this is okay. This is a clock gate data check. This is a data path. So this is from flop to flop. I have not drawn here, but you can see the start. Okay, no, not the flop to flop, but input to a flop. So where you are saying like I have an input called MOSI. That MOSI input is connected to a flip flop inside, and that is current state. So how I want to see this,
and without
like
check or counteraction, it was neutralized and foiled when confronted by the strength of Lord Vishnu, which is Krishna. Krishna did that.
Yeah. So here you are just telling what I explained you before in this diagram. So here you are telling like I have a pin, input delay is there, and that pin goes to the some D flip-flop. So basically what it's saying, like the data which is launched by this input port, it should settle before this clock edge, which is appearing at 4, it's a slack time, the launch clock, and there is a capture clock, which you should see. Okay, yeah. So here you see capture arrival time. It's a 500 nanoseconds, and next clock is coming. Sorry, read this as a like this. Launch clock is appearing at 500 nanosecond. After adding this latency, it becomes 505.7 something nanosecond. The input launch clock, sorry, delay, and then capture clock is coming at around 1000 nanoseconds. So data should be stable, and if it is not stable, it will give you a violation. So this is quite relaxed path because my input delay is like 60 picosecond, 60 nanoseconds. So relative to a timing window, it's quite relaxed. This is similar path, but this is from input to flop, but this is from flop. Okay, this is from actually from input port to output port. So it's a combinational path. So it's a directly, how it looks like is a start point, it's SS pin and directly going out to meso pin. And this is, if it did not respect timing constraint, then it will violate as well. I should have some violation report as well. But then the diagram which you see, the violation is basically you are not respecting this fundamental motivation that data should launch on one clock and capture on next clock edge.
Hello.
Yeah.
Hello, sir.
Yes.
We have to actually close the session. Okay, near about 9 o'clock. Okay. So
Yeah,
how many slides? How many slides are remaining?
I'm pretty much done. So what time it is? How much time I have?
It's now actually you can take a 5 minutes. Okay, then we have the question and answer session with participants.
Yeah, okay. Then I will go
Okay.
fast forward. It's okay.
Okay.
Yeah. Then you have a gate level simulation. Then you have a RTL, synthesized netlist. Basically, you can run same test cases as I said, like, and or you have a formality where you have a design and then synthesize netlist and the guidance file if it has performed any synthesis trickery, and then formality will tell you pass and fail. What formality will do, like it will take the RTL, it will break the RTL, its own internal synthesis engine. It will take your netlist. It will do one-to-one mapping based on naming or by other naming rules, mapping rules. Then what it will see, like it will try to see, like if I try to, these are the vectors. If I stimulate these vectors to this logic cone and this logic cone, the capture value should be same. So it's more static verification. But this is a formality tool. I don't think so you have any open source tool for this, but this is good to have. Physical analysis, physical synthesis, basically this is the where you will get into a physical domain. So basically you have a synthesized netlist, you have a technology library, you have a parasitic extraction, power and ground. And then you have an output coming from the physical netlist. So what it will do, you will read in this design, And then you will specify, again, you will read library in all possible corners. Left, you will define VDD and ground if you are not defined in the UPF or CPF format. So you have to do this craftsmanship on your own. And then you will initialize design. That's basically creating a database. And then you will do this, you will tell like all this VDD and ground is going to connect to the VDD and ground of this D flip-flops, AND gates, OR gates, standard cells, whatever you have. And if you have some special cells in your design, let's say memory or something, then you have to explicitly tell connect this to the memory power memory ground. So it's a connect global. Here you will specify the floor plan. So here you will actually specify the width and length of the final, basically. Then this is no point you can go back. So this is a final specification of a die, what is width and what is length. And then using edit pin, you will place the pins. These are mostly driven by the design specification because they know what they want to do on the PCB board with this chip. So they will basically tell you where this pin should go, left side, right side, top or bottom. And then you will add power ring. So the net which you have created, it will create a power ring so that you can connect to that power ring by VDD and ground. I will show you. And then you will create a power stripe. So basically you will create a strong network of a power. And then you read a def file of a synthesis, which I told you, you remember, this is the def file which it's created. So what it has, like which scan chain looks like, this flip-flop is connected to this flip-flop. I will tell you why you need it. So basically, this is the basically add ring. So after you add ring, after this command, it looks like this. You create VDD ring and the ground ring, and then you add stripes so that it becomes like more. So if you have a 3 volt here, you have 3 volt here, you have 3 volt here, you have 3 volt here. These are the very fine wires. They are highly resistive, so you have to have multiple tappings so that you get pretty much same voltage everywhere. So this is basically a tapping to maintain strong ground and strong power. And these are the blue lines. These are the channels where you will place your physical nets, because physical nets are made like they are rectangular shape. Top level is a VDD, ground is a power, bottom is ground. So you will place exactly in the middle of these black stripes so that they will automatically get VDD and the ground. So then you are good for, so basically we spend more time in floor planning here. This is a crucial time. You can say more than 50% time is spent here of the design to really get this final concrete. Then you will place it. So here you see all these rectangular blocks. Those are flip-flops and the gates, they are placed. And as I told you, it's not shown here, but these lines, these are VDD and ground. So VDD and ground is already connected by placement itself. And then we perform add ties. If you have a constant logic, like constant high or constant low, we don't want to directly connect to VDD or ground. So for that, we have tie cells, because VDD and ground can be a noisy. So we don't want to connect gate of a cell to directly to VDD or ground. So here we go through the tie cells. Then we perform optimization and pre-CTS optimization and checks. So basically, we want to make sure that we are not doing anything which is not manufacturable. Again, which is manufacturable here. So if something is their problem, it will tell you, okay, fix this because I cannot fabricate something like this. And then here you will perform clock tree synthesis. So in the clock tree synthesis, if you remember, I said 4 nanosecond. So what I said, like if this is my clock pin, all the clocks to the D flip-flops should go within 4 nanosecond, or more or less exactly at close to the 4 nanosecond, so that the digital design principle is intact, that every flop get the clock at exactly same time. So we want to uphold that principle. So after that, it looks like after clock tree synthesis, clock tree look like this. So I have, let's say, more than one clock domain. So you can see one clock domain. So these flip-flops, they are going to talk to each other. So you can see this clock tree is pretty well balanced to around 3.5 nanosecond. This clock tree, these are the flip-flops, red color. They are going to talk to each other. So these flip-flops, they are pretty well balanced. So all clocks, they are going to get around 3.5 nanosecond. This clock domain, which is going to get clock at around 2.5 nanosecond. And we did not perform any optimization because they are not really talking to each other. And if they are talking, they are handled by optimization. Here, this is actually physical script for a routing. So here actually you will perform routing. So, and you will add filler cells and decap cells. So filler cells and decap cells, because there are lots of area which is empty. We don't want to keep this area empty because manufacturing limitations. So we want to add this physical only cells. So we get kind of good density of the cells, even though they are not doing any logically. So they are just sitting there so that they help manufacturing capacity, manufacturing process. So here you see it's a detailed routing. So all routing is done. So this is how chip will look like. And then here you will perform GDS. So this is actually a file that goes to the fab, and you get a power ground netlist where you can get SDF file for accurate delay, including wires. So basically here you go for in-house verification further, and you can send this to your foundry. And if something happens after sending foundry, you can still have a possibility called engineering change order. So where you can do handcrafting, where you can change some metal layers and something like that. This costs you, but it's less expensive than changing something here in the bottom layer. So this is the physical area. After physical area, you should get more or less same timing reports, but those are more accurate now. You don't see any 4 nanosecond information which I kept here. Here you get actually what you see in the design. So this is the timing path here. It says like this clock gets 8 nanosecond here. This flip-flop to this flip-flop, it gets 14 nanosecond timing path is met. So now after that, it can generate another. You can use now this netlist and this SDF file and kind of run meaningful test case where your chip will run in whole of its life and generate meaningful activity. That meaningful activity, go and you will give it to as an annotation and not some statistical activity. And that will give you like a real power, real close to your application, what power you expect. Now you see this flow. You start from RTL, UPF, you go to a synthesis, you get synthesized netlist, UPF, then you go to place and route tool, you get place and routed PG netlist and UPF. So you can perform the formal equivalence check between these two guys and these two guys. So basically indirectly you're performing check between these two guys. But life is not simple. Even though you're trying to manufacture something like this, what you get is something like this. So that's why you have to perform test like stuck at fault or transition fault. Now, if you remember, this is a testing tool which we use for performing the fault testing. So, and how we will perform this fault testing. If you remember this file which I have generated, this is the test protocol file, still file. We can use this file because this file will give us a test protocol. So here you see this file goes somewhere here. This is the still scan protocol file. You have some ad hoc tools and it will get translated into the tool which you are using, some vendor tool. So here I'm using some Tesson tool, which is Mentor Graphics Former. So you have some ad hoc script provided by them. So it get translated into this do formats and this protocol file. So basically this will tell like how the tester will put this, how tester will control the test pins. Once the tester will control, once you pass this information to a tester, tester will generate patterns for you. And tester will generate patterns for you for two type of faults, stuck and transition. So here I'm just giving you stuck description. You will exactly repeat this for transition. So what it will do, basically, it will perform some chain test. Chain test means first it will not do anything, but it will just perform, it will perform 11001100. That is chain test. Why it's 1100? Basically, it's performing all transitions: rise to rise, fall to fall, high to low, low to high. So 11 is rise to rise. 1 to 0 is high to fall. 0 to 0 is fall to fall. So this kind of transition. So it will test that. And test mode, in scan test, what it will do, it will get into a shift mode. Then it will get scan enable. It will fill in whatever data it wants into a shift register. It will give 1 clock cycle. So the data I will show you directly in picture. So this is stuck. So you get this design. You control scan enable, and you perform some scanning pattern. So you scan in 0 and 0. So now all these registers, you're getting 0 and 0. Okay. Now you will go next step. You will give 1 clock pulse. So data will propagate from this flop and will capture here. Let's say this is inverter sitting here, and you were sitting already holding this pin again 1. So this will capture 1 here, and this will capture the 1 which is simulated through this inverter. And then you will go back. So you will scan out that 1, 1, and at the same time you will fill in new scan data. So this process will keep on in repeated process. Okay. So this is basically a flow, how will it look like for scan testing. For transition testing, it will do exactly same, but what it will do here, it will perform 2 or more clock pulses, so that data will move as a like a transition, like 1 pulse and second pulse, and it knows like what it is doing here. So this is the key here, and in the end, it will give you kind of report. What I want to show you here, it's a time-consuming process. So you can see it takes 93,000 seconds to generate these patterns here, and for transition patterns, it takes like 500,000 seconds. So it takes like more than 1 day here for this, and for transition patterns, it took a week to generate just patterns. It's a very computationally intensive process. So you need many cores. That's how life is. You cannot cut corner here. Now you have a test bench. So you have a test vectors. You have a test bench generated by this tool, and then this Session tool, you will just go to the Xilium, which is event-driven simulation, which you use for your RTL simulation many times. You have a SDF. So how will it look like in slow mode, in typical mode, in fast mode, and you will simulate this. Okay. So basically, you are checking your patterns are working fine. So most likely, it will always first perform this scan test. So this chain test. Chain test is basically just pipelining through this flip-flop shift register. So whatever you're feeding in, seamlessly coming out. So that means your chain is intact. This is how a test simulation look like. So after your simulation is done, now you get these wafers by after 4 months, 5 months, whatever time it take. You have patterns at your hand. We are a test company. We are a tester also. So now this goes to the something called ATE. So ATE will have all this. You will pass these wafers, of course, automatically. You will pass these patterns. So ATE will perform this test, and ATE will kind of make these dies, like which are good dies and which are bad dies. And then it will goes to the dicing. So it will keep dicing. It will throw away the bad dies, and then it will do the bonding and the packing. And you get the final ASIC out. So that's all from my side. It was fast forward in the end. I'm sorry because of time, but what I want to tell you is nothing is showstopper. Feel free to download these open source tools. Get your hands on those tools.
हिंदी लगा सकते हैं, डिफिन लगा सकते हैं, ना कुछ कर सकते हैं।
Hello.
लेकिन बहुत अच्छा लगता है।
Hello.
काम काय होत नाही।
Yeah, I cannot. Yeah, okay. But this is the. If you have some time, I'm over time. I'm sorry.
Correct.
But this is what I have for you.
Thank
If
you,
have any
sir.
questions,
Thank
yeah,
you.
or we can-
Thank you. It's a really in detail lectures. We have revised many concepts in ASIC design. So now the session is open to the participants. If you have any questions, please unmute and ask. Otherwise, put in the chat. Okay.
Yeah. Sorry.
Meanwhile, I have some questions. Okay, how your functional verification and design for testability, whether these are two different concepts, and
yes, functional
how there
verification
is
a
okay.
Yeah. Tell me. Sorry. Yeah. Tell me.
What should be the flow? Means you are doing functional verification first and then DFT, or DFT first and then functional?
No. Functional verification first. When your functional verification is good enough, you
Okay.
go for synthesis. In synthesis, you insert DFT. So first, functional verification is actually you're running functionality, checking functionality. If your chip is, let's say, for sake of simplicity, if your chip is, let's say, SPI only SPI. So your what chip is doing is basically respecting SPI protocol, reading, sampling data properly, storing data in FIFO, and transmitting that data. Scan is completely independent. Scan is, it doesn't matter whether your ASIC is SPI or processor core or another state machine. Its job is to just make a shift register. So ultimate job is to make a shift register. So what test want? Test says, like, I don't care about this cloud or this combinational logic. What I want full control on clock pins. I want full control on reset pin, so that I can control these D flip-flops. And then I want to have a capacity so that I can set these D flip-flops to the known state. Once I know these flip-flops at known state, I will trigger them by sending one clock pulse. Then that time it will go through this combinational block, and then I know what I'm capturing, and that is depending on this cloud. And I'm checking this cloud indirectly. And if something happens bad in your design, as you show, you are aiming for this layout, but you're aiming for this metal layers, but your metal layers actually happen or fabricated like this. So sometimes the metal layer will become like get shrink. The metal layer will toggle, but it will be slow to rise and slow to fall because it will become very resistive. Sometimes it will become completely open and it will get stuck to a logic value or some kind of a weird state. So that test we are doing. So DFT is basically what I'm checking is a whatever logic we have in this cloud. We don't know what that logic is doing, what kind of functional job is doing. We just know the basic functionality of that cells. Like if it is inverter, then I expect it's inverted output. If it is buffer, then I expect non-inverted. And if it is some fabrication defect, then I see some weird behavior. And based on that, I will throw that die. It doesn't stop here. It will go actually in HTOL tests. I mean, if your ASIC costs like less than $1, nobody goes to HTOL test. But if your ASIC costs you less $100, like a processor or some kind of a medical chip, diabetes, blood monitoring, sugar chip, then they go for HTOL. HTOL is basically, I don't have a long form in my head. It's a high temperature something. So basically they will put this chip in a baking oven. It will raise temperature to a certain degree of a 45 degree, 45 degree, 80 degree, whatever application area is, and then take that out chip and then again try to run patterns on those chips.
Okay, I have one more question basically. So you have very vast experience in ASIC design right now. So from your point of view, okay, while designing your ASIC implementation, so which stage of your ASIC design you feel most critical? Something like synthesis or placement or routing. Which stage you feel it is very difficult to synthesize?
Actually, the thing is, like in industry, they want to capture problems earlier because this whole cycle takes long time. So that's why they have a linting checks and all these checks. So basically, they want to detect problem as early as possible. So
No,
if
but
you
it's I'm just asking from your experience. So at which stage you feel difficulty?
timing closure in the backend is a difficulty, because if you go to the lower end technologies, that means if you go into like less than 32 nanometer, apart from physical cells, you get physical only cells. For example, tap cells, well taps. Those are basically cells which you have to implement just to fabricate chip. And why those are important? Because basically whatever P wells, N wells they will make, they have to respect these physical properties. And then basically you are basically getting area critical, because your die is filled with functional blocks as well as some physical only blocks. And if you don't meet timing there, then either you have to perform ECO. So what you have to do, basically you have to go to some kind of specific timing. If this timing is not met, for example, in my backend. So what I will do, instead of going through all the process, I will report this time. And then I will see, like, for example, here I see one inverter in the end, which is X1, which is low drive strength. So what I will basically swap this inverter manually, or by even it's tool command, but manual tool command, and change this inverter to X2 basically, or X4 for that matter. And then try to fix that timing. So basically, more you go in the backend, more critical it becomes.
One last question from my side only, ma'am.
It's
That is
already 9:30. We can connect one-to-one.
correct. Phylastic design. So have you come across any such a kind of problem here? Some issues get escaped from pre-silicon verification, and that get appeared in the testing itself.
Yeah, I have one very good example that I have experienced and been through that problem. So, this power grid, we try to make it as strong as possible. But while making power grid, there is a one concept is like not my entire logic is going to toggle at the same time. So I don't need a strong power grid. Even though, let's say, if I have 10,000 instances, all 10,000 cells are not going to toggle at the same time. So some people try to not pay enough attention on this power grid. But now see what will happen here. When you will go into a test mode, you are in shift register mode. All these scan chains, they are toggling at the same time. So basically your power grid should be strong enough so that it can provide enough VDD and ground, clean VDD and ground to entire circuitry. Otherwise, they have to do some workaround. So what they will do, they will generate patterns such that if you have multiple scan chains, so they will at the time of cost. So they will fill in first scan chain with data, then fill in second chain with data, then fill in next scan chain with data, and that will cost you a time. And normally the companies will expect like 4 to 5 seconds. If it is a DSP processor, for example, they expect 4 to 5 seconds for testing one die. But if you have to do this trickery, that you're filling like first chain, then second chain, then third chain, then your scan timing can go from 4 seconds to maybe 7 seconds, close to more than 50% more, 30% more, and that can cost you money. I mean, the company can.
Okay, sir. Thank you.
This is one scenario which why you need a really strong floor plan or strong power network. But yeah, this is what I have. It's a fast forward in the beginning, but yeah, in the later stage. But that's what I have for you. If you have other question, then let me know.
No, sir.
My side
now
is
we
over.
should thought.
Okay, so ma'am.
Yeah.
Just give the vote of thanks.
If any other questions are there, we can one-to-one communicate with him.
Yeah.
I'm sorry for that, but then it's already 9:30.
Yes, it's fine.
Yeah, okay. So to stop this, I would like to extend our sincere thanks to you the esteemed guest of honor for today's ATAL Faculty Development Program session. Your comprehensive expertise spanning RTL coding, UPF, then UBM synthesis, FPGA synthesis, DFT, low power simulations, placement and routing, static timing analysis, on sign off checks greatly enriched the discussions. The way you translated complex VLSI concepts into practical industry related insights was really truly commendable. Like the time is not enough for you to explain your experience, but then it is a time constraint which we require you to stop here. So your session was not only strengthened the technical understanding but also inspired faculty and participants to align with current semiconductor practices. So on behalf of the organizing committee, we deeply appreciate your valuable time, knowledge, and engaging interaction. So thank you once again. And we will be communicating with you for more sessions in depth whenever we require. So thank you once again.
Yes. Yeah. And
Thank
I
you,
will
Sagar,
say,
sir.
get your hands on open source tools. I will be very happy if faculty can use that in their
Sure.
curriculum.
Yeah. We can have, like, you can mail us the open source links so that we can share it
Yeah,
to
I
the
will send the
participants.
presentation. They are in presentation. Yeah.
Right. So nice. Okay, sir.
Yeah.
Thank you,
Thank
sir.
you once
Thank
you
you
again.
very
very
much. Yeah.
much. Thank you.
Yeah.
I
Bye
also
bye.
thank.
Have a nice evening. Yeah. Bye.
Bye. I thank to all the participants also for their patience and enthusiasm. Thank you all. Here we conclude the session. Thank you.
Yeah.
Hi, hello, Sagar.
Yeah. Should I? I'm using Zoom first time, so I don't know what
Okay.
exactly. Yeah. You can talk if
You had delivered really well. Okay, and it's really in detail. Okay.
Yeah. I spend a little bit more time in the beginning. So, but actually, later part is more tooling part. You can easily understand. That's not
Okay.
really big deal. Yeah. So, should I sign out?
Yeah. Yes. We have
Okay.
a communication afterwards. Thank you.
Yeah.
Thank you
Bye.
very much.
Yeah.
Thank you. Bye.
Yeah. Bye. How I can do that here? Just close.
No, I will
Give meeting.
just
Yeah.
I will
Okay.
close the meeting. Okay.
Yeah. Thank you.